Wonderful. So I think we have more people join, and yeah, I think one thing is, let me see. So in our system, actually you can see a lot of materials there, so that maybe you want to have a check out there. Yes, week. Here it is. So for this tutorial, actually you can see at the bottom of our session, actually we have a handout, and we contain a QuantumFlow flare, and here we give some information of this tutorial. And the most important thing that we have a lot of resources here. And for example, if if you have some trouble to connect to the Google Colab, actually we suggest that you can deploy the package on your own on your local side, so that you can see when we're doing some tutorials on the codes and on the hands-on, you can also follow with us. But first of all, maybe you can try to make sure that you can connect to the Google Colab. We will heavily use it. Yeah, I shared in the chat, but we have more people coming a little later, so I put the link there again. Okay. And yes. Good. I think it's already 9 o'clock, so maybe let's just wait for 1 or 2 minutes, then we can start today's tutorial. Okay, great. Yeah, hello everyone. It's very nice to see you all in this actually in the morning on my side, maybe in your afternoon or evening, depends on the and today we are very glad to present our QuantumFlow work. That is a co-design framework of neural network and the quantum circuit towards the quantum advantage. And yes, this will be our first session. And in this session, we will do some introduction to the quantum computing and machine learning. During the tutorial, feel free to unmute yourself and ask any questions or answer the questions from my side. And I am very happy that if you can join us and do some interactive, that will be very helpful for us to communicate and to learn something. And first of all, let me introduce myself a little bit. My name is Weiwen Jiang. I joined the George Mason University in this year as an assistant professor. And my education background is that I graduated from Chongqing University and obtained my PhD. And during the last 2 years of my PhD, I conducted research at the University of Pittsburgh. And after I graduated, I do the postdoc at the University of Notre Dame. And during these 2 periods, actually, I do a lot of research on the hardware and the software co-design on the neural network. And we proposed the first hardware and software co-design framework using the NAS, that is a neural architecture search. So we do a lot of hardware and software co-design, and we proposed the very first hardware and software co-design framework, FNAS. And the FNAS was obtained based on paper nomination at DANC and also TCAT this year. And also we built up a lot of things on the FPGA stuff, and one of them obtained the base paper nomination in the Qubits and the ESWEEK. And another thing is about the NAS and the NOC, that is network on chip, also obtained the base paper nomination on HP DAC. During the past 2 years, actually, we built up such kind of stack for the hardware and the software co-design. And this one are used for the classic computing stuff. We based on different hardware, FPGA, ASIC, and computing in memory. So you can see that my background is on our EDA society on the code design, hardware and software code design. So I believe that this is one reason we moved forward, and when we consider quantum computing, what quantum computing have, and how can we use quantum computers. Actually, we are also think about such kind of approach, and that is we can do the hardware and software co-design. So recently we moved to the research area as quantum machine learning, and we want to build up such kind of quantum machine learning system using the co-design philosophy that we applied for the classic computing. And so this is a very nice graph that is used the entanglement of the qubits. Actually, for the quantum computing, there are two basic ideas that is very important. The first one is superposition of the qubits. So each qubit, as you can see, it has a superposition. And another very important idea is that the entanglement between or among qubits. So this graph shows that all of these qubits are connected with each other, and also they are entanglement with each other. So what's the meaning of the superposition and the entanglement? We will demonstrate it a little later in our first session, that is the introduction session. Very nice. Actually, this is our collaborators. Actually, we are also like the quantum computer, like the qubits. We are entangled with each other to do such kind of research. And I would like to introduce my collaborator a little bit. Actually, we are collaborating with Professor Yi Yushi from the University of Notre Dame, and his student Ziding. Actually, he did some job on the QuantumFlow robust neural network. This is very important because today's quantum computer also has a very high noise, so that we need to consider how to conduct the neural network in such kind of unstable environment. So this is one work from their side, and we also have the collaborator Jiang from the University at Buffalo. We have the collaborator Lei Yang from the University of New Mexico. And on my side, actually, we have a lot of students doing the quantum stuff. But for now, our contributor for this tutorial include the Zirui, who helped to develop the API stuff so that you can use the QuantumFlow very easily. And we will introduce the QuantumFlow a little later. And we also have the member Zepeng who do the stuff on the QF mixer. That is also a very interesting topic, and we will touch it a little later in today's tutorial. So here is our quantum works during, I believe, just this year. Actually, we started from not this year. Actually, I believe year or 2 years ago. And now we have some publications on the quantum, and the very important one that we will touch today is the QuantumFlow that is just published this year in Nature Communications. This is the first co-design framework for the neural network and the quantum circuit, so that we can have the potential to achieve quantum advantage. So I believe we have a lot of new concept here. So what is the meaning of quantum advantage? Okay, so we will also see some definition, and also what is such kind of stuff a little later. And we also have some publication at SPDank and SCCAN. So because we are from the EDA area, so that we have some publication in this area, and to enrich the topic in such kind of area. And also we are invited to give talks and IBM Quantum Summit last year on our QuantumFlow, on our co-design framework. And also this will be our today's tutorial and ESWEEK. And in the next week, actually, we will also have another tutorial on the quantum week. So this is a whole picture of what we have already done on the quantum stuff. Okay, so let's see today's agenda, and the first session will be the introduction. I will introduce the quantum computing at the first step. So we will starting from the classic bit to the quantum bit, that is also known as qubit. And we will also starting from the logic gate to the quantum logic gate. So that when we do the, when we manipulate the classic bit, we use the logic gate. And when we do something on the quantum stuff, do the quantum computing, we will manipulate the qubit. So we will apply the quantum logic gate to manipulate the qubit. And after that, actually, I will give you some hands-on the basic quantum gates, so that you can see how can we operate how can we construct the circuit to do some task on the quantum computer. And this one will based on the IBM Qiskit. After that, I will give you a brief introduction to machine learning. I believe a lot of you may have the background on machine learning, so that we will just go through a very basic version. And after that, I will go through the history of the quantum machine learning and introduce different quantum machine learning approach, and also the design and also the history. So we will give some motivation and also the very basic data encoding stuff. After that, we will introduce some algorithms, some quantum algorithms to implement the machine learning stuff. And in the second session, we will introduce the QuantumFlow. That is a very general framework for the co-design of quantum computing and the neural network. And after that, we will show how can we apply the co-design philosophy to achieve quantum advantage. After that, in section 3, we will introduce the most recently developed API for the QuantumFlow, that is named QFNN, and we will show how can we build up a quantum circuit based on such kind of library to directly implement the neural network on the quantum computer. And the section 4 will be some extensions. We will introduce two of our recently work. That is, one is a QF mixer. We are trying to explore the quantum neural architecture, like the classic computer architecture. We have NAS already. We have the very powerful tool. But now when we move to quantum, whether it is so easy to explore the quantum neural architecture, actually it is not, because there are a lot of limitations on the quantum physics. So that we want to explore the base new architecture that is suitable for the quantum computing. So this is one known as quantum QF mixer. And the next one will be the QF robust NN, as I mentioned, because the current quantum computer has a high noise, it will occur some errors. So that we need a robust neural network so that it can work on the quantum computers. And finally, we will give actually in this session we will have some open question and discuss some future work. And last the last session, actually, we will finalizing this tutorial, and we will mention about something about a special issue of quantum machine learning and electronics. And I think this is some flavor for such kind of special issue. I am one of the guest editors. Okay. So come back, actually, I believe some of you have already seen this, but some of you may not have the opportunity to see this. Maybe at this point, I can again to share this link for you. So the very first one, Colab, that it will be our platform to run our codes. This is nice because you know that we do not need to do some environmental configuration on Colab, and you can directly run our code on the website. And the second one is the GitHub of our today's tutorial, QuantumFlow tutorial. You will see a lot of codes here. For each session, we have different code, so that we will use this code later. So if you have some trouble to access the Google Colab, we suggest that you can copy, you can clone this this GitHub repo to your local site and install some required package that is listed here, so that after you configure this, you can also run the code at your local instead of on the Google Colab. And the third thing we want to mention is about the Kirk. And actually, this is a very simple to use simulator for quantum. Actually, when I do a lot of research on quantum computing, at the first I do not understand a lot of operations in the quantum gate, and this one will help you to simulate. For example, if we want to have some quantum gate, and also we want to see the amplitude, some state of the quantum qubit, it is very easy for you to see something from this simulator. So I recommend that if you want to do some research on quantum computer and you want to learn something, maybe this one will be a very powerful tool for you to learn something. And the last one is a Qiskit, that is a IBM Qiskit, because you know IBM provides the real quantum computer, and if you want to use their quantum computer, they provide such kind of interface for us to access the quantum computer. So this one is also the backbone stuff for our tutorial, for the things that we build up. So this will be some tools that I would like to introduce to you. And if you want to have a try of our code, maybe you can, either way, you can, if you can access Colab, that will be perfect. And we can directly run it on the browser. And if you do not have the access to Google, maybe you can have a try of the, to deploy this GitHub repo into your local. Great. So I think that is enough stuff for the beginning and also for the preparation. And so let's enter something about the quantum. So what is quantum computer, and why we need a quantum computer, and what's the difference between the quantum computer and the classic computer? So we will go through. We will start from the very beginning. So what's the data representation in quantum computer? I will not give you a lot of big picture on how benefits that we have, but we will see this a little bit. So this one is the roadmap from the IBM, how their quantum computer will grow. Today we have the Hummingbird that was launched last year. It has it is a quantum computer with 65 qubits. And it is deployed on September last year, and it is expected that we will have more than 1,000 qubit in 2023, so that we will have a more powerful quantum computer at the end of the day. Yeah, so yeah, actually I see a question from chat. So for the slides, it will be available a little later on our website. So let's come back to the slide. Actually, you can see that we will have a very exponentially growth on the number of qubits. So what is the information behind such kind of growing, such kind of trend? So let's see the qubit and the classic bit and the qubit. So basically, for the classic bit, actually, as we know, it is a binary bit. It can represent 0 or 1 at one time. So for each time, it will represent only one state, that is 0 or 1. And for qubit, for the quantum bit, it has two states, that is a 0 state and a 1 state. So we have 0 and 1. So what is the meaning of 0 and 1? That means we can have both states at the same time. And for each state, it has an amplitude. And this amplitude is associated, for example, A0 is associated with state 0. And the thing behind this is that when we do the measurement, actually we will extract the information from the qubit. It has the probability of A0 square to obtain the 0 and A1 square to obtain the state 1. So during the processing before we do the measurement, actually we can have 0 and 1 state to be exist at the same time. So this is a beautiful thing of quantum computer. We will not only present 0 or 1 at one step, but we will present 0 and 1 at one time. So and okay, so you can think of okay for 1 bit, okay, so what? It is just something like we have 1 bit, and so for quantum it can present 2 bits. But think about this: if we have a large number of qubits, as we mentioned for quantum IBM quantum, it can provide more than 1,000 of qubits. So how about the collaboration of different qubits? Whether it can make a big difference? The answer is yes. So for the multiple qubit, for example, for 2 qubit, actually you can see we can for the classic computer, actually we can only present 0 state, or 0 1 or 1 0 or 1 1. But for 2 qubits, we can present a 4 state at the same time. So when we scale up to n bits, so for quantum computer, actually we can present 2 to the power of n value at the same time. But for the classic computer, we can only present one n bit number, or we can present n binary number. So you can see this is not just a 2 compared with 1. This is 2 power of n compared with n, or compare with order 1. So this is the most powerful thing of quantum computer. Actually, we can store a lot of information in such kind of a combination of quantum bits, the qubits. So on the right hand side, we present some basic stuff for the qubit. And before that, maybe we can see this slide a little bit. So for the presentation of a qubit, actually we will use such kind of a vector to present the state. For example, for the state has the amplitude of A0 on 0 state and A1 on 1 state, we can present it in such kind of vector form. And the first one is associated with amplitude of 0. So that is associated with the state of 0, and A1 is associated with the state 1. So we have such kind of vector to present the amplitude of both state 0 and state 1. And initially, for a lot of quantum system, like the IBM quantum system, actually we have the initial state to be 0. So then we have such kind of formulation, like the first one, A0 will be 1, and the A1 will be 0. I see 2 questions from the chat. Oh, there are only 7 real devices, right? No, actually, I believe even so the first question is whether there are only 7 real devices right now. So of course not. I believe just in IBM it provide more than 7 real devices. Would you? The second question about, would you illustrate what is the difference between readout error and probability means 1 prepare 0? So about the readout error, I believe that we will have some discussing at the very end, the QF robust neural network, that will discuss something about the error in the quantum in the qubit, and so maybe you can say something at that part. So let's come back. So this is our so if you have any question, maybe you can unmute yourself so that we can so our audience can hear your question, and we can have a better discussion. Okay, so come back to this representation. We can see that we use such kind of vector to represent the state of a quantum qubit. And how about we have multiple qubits? So now we know that for each qubit, for example, for Q0, we have such kind of state, and we can represent it using a vector like the A0 and A1. And for Q1, we have another state that is composed of B0 and B1. So when we have 2 quantum qubit, we have 2 qubits. So when we do the combination, actually we use the basic operator that is a tensor product. So for tensor product, actually, what we do is that we can combine these 2 states and to generate the C stuff here. And from one understanding using the probability, you can see, so for 0 and 0 state, for 0 state, actually it requires both Q0 and Q1 to be in the state 0. And you know that for the for this representation, actually we have the amplitude before each state, and the square of such kind of amplitude will be the probability. So that C0 square represent the probability of the both qubit 0 and qubit Q1 are in the 0 state. And for the given Q0 and Q1, we know that the probability of Q0 to be 0 state is A0 square. That is the probability. And for Q1, that is a B0 square. And they are independent with each other. So that when we calculate the probability of of Q0 and Q1 to be 0 and 0, and we can do the multiplication between these two probability. And when we transfer it back to the amplitude, we do the square root on such kind of probability, and then we can obtain the C0 and 0 to be the result of A0 times B0. So this is a basic idea of how can we formulate the C0 and 0, how can we calculate its value. But the thing behind this will be the tensor product, as I mentioned. So for the tensor product, actually we will have such kind of formulation, and Q0 is represented by this vector, and Q1 is represented by this vector. And for the tensor product, we will have A0 times Q1 and A1 times Q1 again, and then we can have such kind of formulation, and this is totally consistent with what we have at this place. So I want you to understand a little bit of such kind of math, because you know this will be the fundamental things in quantum computer when we have multiple qubits, or when we want to operate multiple qubits. This will help you to understand a little bit. So this is just some little math. As I said, if you have any questions, feel free to unmute yourself and ask a question. Okay. Any question at this moment? If no, maybe we can move on. If you yes, we can stop a little bit to clarify something. Okay, great. If there's no question, maybe we can move to the next part about the logic gate. So now we have qubit, and the next thing that we want to operate, we want to manipulate this qubit. And we know that for the classical circuit, actually we have the logic gate, like we have the NOT gate, we have the AND gate, the NAND gate, the OR gate, and the NOR gate. We have a lot of logic gate. The similar thing on the quantum computing, we also have different gates, like the poly X, poly Y, poly Z, Hartmann gate, phase gate. So the basic thing is that for the classic computing, actually we have the truth truth table to see if we have two input, if they because we know they are binary number. So for example, for AND gate, if we have 0 and 1, what will be the output of such kind of input? So this will define the AND gate. On the quantum side, for the quantum gate, actually, because you have already seen, we are not only have the binary number, we have a vector. So the whole thing behind the mathematical for the quantum computing is that we will do the matrix multiplication. And more specifically, because you know our state is represented by a vector. So we will, when we operate one qubit, for example, this is a qubit Q0. When we operate such kind of qubit, because Q0 has its state, right? We already know this, right? And when we want to operate such kind of qubit, like we apply an X gate on Q0, what we do is that we will transit the qubit from the one state to another state. So this is what we do on the quantum on the quantum gate. And the transition between these two steps is based on the matrix multiplication. More detail, for each quantum gate, it can be represented by a matrix as demonstrated here. And what we will build the connection between this conversation is that we will apply the matrix times the current state A0 and A1 to obtain the output state, that is B0 and B1. So we can build up such kind of connection. So this is how quantum logic gate works. It will apply on one qubit and converts the state from the previous state to a new state. So this is what we have for the to operate the qubit on the quantum computer. And you know that when we want to implement some function on the classic computer, we will build a circuit. We will use a combination of this logic gate to build a function. Similarly, for the quantum computer, the basic stuff is that we have the quantum gate, and then we will build up the quantum circuit to implement some function. So this is basic stuff on the quantum circuit and the quantum gates. And in order to understand more details, actually, we would like to introduce this gate a little bit instead of just seeing this that picture. And during this period, I would also like to show you how can we construct such kind of gate on the Qiskit. And so let's first see the single bit gate. So for example, on the logic side, on the classic side, we will have the NOT gate, and it transits for example, the input of 0 to the output 1 or 1 to 0. So this is the classic stuff. Now let's see what our quantum NOT gate do. So this is known as X gate, also the NOT gate on the quantum computer. So this is our first. We can see this is our first gate we want to see. And for example, because we know that the initial state of a qubit will be 0, that can be represented by 1 and 0. And we know the representation of a quantum gate like the X gate is in such kind of format. So when we do a little math on this stuff, we can so we will do the multiplication between the matrix and the vector, and we can see. Okay, so for the first line, it will be 0. And for the second line, actually, we will have 1. So we do the similar thing on the qubits, but the thing like that, we not only transit 0 from 1, 1 from 0, but we transit from the state 1, 0 to 0, 1. And we can see for this stuff, if we write it down based on what we have already learned, so this will be the B0 associated with the state 0, and this is B1 associated with state 1. And when we have the output state of this qubit at this place, for example, let's say this is a fine, and we will have the state to be like this one. So we know this one will be 0, and this one will be 1. So we have the final state to be 1. So we do the similar thing to flip the state from 0 to 1 using the X gate, right? So we can see they have some correspondence, but for here, what we do is that we do the matrix multiplication between a matrix that is that to represent a gate and a state. This is our initial state, right? And then we can obtain our final state. So this is the operation in a quantum computer instead of what we see on the classical ones. Okay, so the next state will be the Z gate, and we will also use it very frequently in our design. So then I would like to point it out. Similar thing, actually, it has its own matrix representation, and when we do the thing on our initial state, actually we can see then we will do such kind of operation. But you can see for this stuff, it will not change the state at all. But if we do some initialization, so if our initial state is not 1 or 0, but the 1 state, Then we will have 0 and 1, and we have such kind of Z-gate. And what we will have is that we will change the sign of the second state. Okay, so the Z-gate will flip the face, but in the matrix representation, we can see it will flip the sign of one state. So this is X gate and Z gate. And I think that we can see our very first programming here, so that maybe you can have a better understanding for the later implementation. So now maybe if you want, you can also open this stuff. I think I can paste the link into our chat so that you can access to it. Okay, so if you can open this this Colab, and okay, maybe you can see that we do some stuff here, and you want to change the is Colab to be true, so then we can run our codes on the Colab. And the very first step that when we want to use the Qiskit is that we want to install its package, and then we want to import the Qiskit, and also we will use some quantum circuit and also AER, that is a simulator from the Qiskit, and the execute we will execute the quantum circuit. One thing what we want to point out is that for now Qiskit has a more newer version, but it cannot support the code that we provide to you, because this code are developed when we test it on 0 to 20 version. So that maybe you want to down version your Qiskit if you already have one. And after we do such kind of thing, we can see that for the Qiskit, actually the very first step when we want to build up a quantum circuit is that we will we will do such kind of thing. We will call the quantum circuit class. Oops. And the parameter we pass to the quantum circuit is the number of qubit that we want to have. And we will have some initial state. For example, we want to initialize it as 1 and 0. And then we will, if we want to place a gate on the qubit, like the X gate, we can call the circuit dot X, so that we can create a X gate. And the parameter here is the number of qubits, the index of qubit. We want to place a X gate. And after that, we can draw the stuff. So we can see if we want to initialize the qubit using the initial state, actually we will have such kind of gates. But as we already see, for a lot of quantum computers, the initial state is naturally to be 0, so that we do not need to initialize it, and we can just place a X gate on it. And we see this parameter controls the number of qubits to have on the quantum circuit. And so if we climb it 1, it has only 1 qubit. If we climb it to be 2, we have 2 qubits. And for example, if we want more qubit, and we just need to change this number, and this number will help us to decide where to place the qubit. If we want to place it on the Q2, we just pass it to 2, so that it will be placed on the third qubit here. Okay, let's go back to our implementation. If we just want to implement the X, actually we X on a qubit, actually we can do it in such kind of thing. And here we have the execution of the qubit on a simulator. So we created the simulator here, and it is based on the AER simulator provided by the Qiskit. And the backend here, we want to see the state vector for the simulation, so that we set this parameter here. And after that, we will get the state vector from the quantum circuit, and we use such kind of statement. And so after that, we will print. Okay, maybe we can hide this stuff. And after that, we will get the state of a qubit. Because now we have only one qubit, we can see we have only one, we only have two numbers, because you know that for the quantum computer, it only not only contains a real number, but it is composed of the complex number. So that this is just one number, and this is the second number, and we can say that it will be the 0 and 1. As what we expected at the beginning, the state will be 1 0, and now we have 0 and 1. This is consistent with what we have already seen from this place. And the following stuff is we can also do the thing using the matrix multiplication as what I wrote. And if we use the tensor from the torch, actually we can create the initial vector and also the Qiskit here, and then we can do the multiplication between the matrix and the vector, and after that we can see they can obtain the same value. And here we just evaluate by compare these two vectors. So this is our Qiskit. And for the Z gate, we will have the similar things. And if you want, maybe you can have a try. And if you have any questions, maybe you can you can speak out, and we can help you out. So this one is when we initialize it as a 0 state. As we see, it will not change the state. But if we initialize it as the 0 and 1, and we do this thing here, and then we can see we will have the negative 1 after the Z matrix. Zero state. So basically this tutorial will give you some idea how we operate the qubit by using the quantum gate. The Z gate is 1 0 1 0, and the initial state will be our initial state. We will run it again, and so here, okay, you can see that this is our simulation result from the after we place the Z gate, and this is what we do on the matrix multiplication, and we can see they will be totally the same. Okay, great. So this is our very first gate to be involved in today's tutorial. Do you have any questions so far? Maybe you can type some question in the chat if you don't if there's some trouble for your microphone, or if you want, you can also unmute yourself. Any questions? Okay, if there are no questions, let's move on. Okay, we have already seen, okay, for now, what we have already seen is that we have the 1 state or we have the 0 state, and they are still represent one value and one time, right? And as we see, the superposition is one of the powerful thing for the quantum computer, for the qubit, because it can represent the number, it can represent the two state at the same time. So the second thing is that we need some gate to push the qubit into the superposition. So the gate that we are going to use is something called the H gate, and also the general gate, the universal gate. The Hadamard gate, the H gate, is has the format in this way. And what we can see is that if we have the initial state to be 0 state, we have the 1 0 for the vector, and if we have the Hadamard gate to apply it on this qubit and to this place, so let's see what will be the state of the our circuit. And what we can see is that we have the this is our coefficient, and this will be 1, because this is 1 1 0, and this will be 1. So now this is for 0 state, and this is for 1 state. So for now, you can see that we not only have the amplitude of 1 on 1 state. Instead, we will have the both state to have some amplitude. So when we say this probability, we can see the probability, when we write it down, that is square root of 2, 1 over square root of 2 on 0 state, and square root of 2 on the 1 state. And if we say its probability, it's the amplitude square, so then we have the probability to be 0. For example, this is cosine, and the probability of cosine to be 0. So the probability will be the square of this stuff. So that will be 1 over 2. So in this case, it represents if we do a lot of trials. For example, if we do 1,000 shots for such kind of qubit, we have such kind of probability to obtain the value 0. So for 1, we have the same probability. So we have 5 times, roughly 5 times to obtain the result of 0, and 5 times to obtain the result of 1. So this is what we have if we create a edge gate here. So we can maybe at this moment, maybe we can go to the IBM Quantum to see something on the edge gate, and you will have a better understanding. Great. And so for IBM, actually, we have the edge gate, and if we can move the qubit to be 1, and then we want to mirror it. Here it is. So for IBM, actually, you can see when we create such kind of circuit, so this is very similar with what we create in the code lab for our first in our first tutorial, right? We have a qubit and we have some gate. So this is in our programming, and similar, it provides such kind of composer, and we can directly drag the gate on the circuit. And after we do such kind of thing, actually we can run it on different provider. For example, here we can run it on the so here is some real quantum computer provided by IBM, and for example here, if we let's first see if we want run it on the simulator. Okay, you can see so this is the number of count to be 0 to outcome 0, and this is the number of count to be the output of 1. So we can see they have a very similar number of runs. So now let's the short is set to this number, and if we set it to 1,000, okay, and we go back to the jobs, and then we can see the number is roughly 500, right? So this means that after we create such kind of edge gate, we will enter a superposition. And if we do a lot of trials on such kind of quantum circuit, actually we can get different number of shots on different state. And also we can run this stuff on a real quantum computer, like this one has only 1 qubit. Maybe we can just try it on this Almond. And let's go back to the jobs, and it is still running. Okay, it maybe take some time. Okay, great. So you can see even on the real quantum computer, we will have also similar result, but you can already see the result are not perfect as what we do in the simulation. This is because the qubit itself has some errors. So if you want to understand more details about the property of the IBM quantum computer, actually you can go back to the service, and it has a system here. And what we so this are the all quantum computers provided by IBM. So it's not only limited to 7 quantum computer, but it has more quantum computers. And let's see. So this one is what we run on the what we run for our previous experiment, and we can see it has some properties, I believe, for the graph view. This is so. For example, there is some errors for such kind of qubit. So this is a reason it will create the result that is not even as what we do in a simulation. Okay, so this is a Hadamard gate, and for you, maybe we can clean this part a little bit. Great. So for the universally qubit, actually we can, so basically actually the qubit can be seen as such kind of sphere, and in the beginning the state will be zero state. We have a state like a vector in such kind of space. If we apply, sorry, if we apply X gate, actually we will rotate the state to the one state. So if we apply, let's change the color. If we apply a X gate, it will change the state from zero state to one state. And the U gate will give us more flexibility to rotate such kind of state. It can be rotated at any places like this one. So we will give some parameter of the theta to rotate and also the fine. Also, we will have the other rotation gate, the Rx gate will help us to rotate this vector, this state along along the X gate. So it will be using this way for the Rx gate. And for Ry gate, it will so this is X axis here, and this is Y axis. So if we initial state for 0 and we want to use Ry gate, it will help us to rotate in this way. The similar thing for the Z gate, it will help us to rotate along the Z axis. So these are the basic gate for the rotation gate. Okay, now we have say a lot of things on the single qubit, and the next thing is about how about when we have multiple qubit, how can we operate this stuff on the multiple qubit? And for example, if we have the two Hadamard gate here, and what we will do is that we will as we have already know, for the initial state, it will do tensor product between fine 1 and fine 2. So if we have multiple gate, actually we will also do the thing like using the tensor product between H gate. For example, if we have two H gate, we will do the H gate tensor product H gate, and then we will have the matrix multiplication for this stuff. And for H gate, its representation is like this one, like this way. If we do the tensor product between these two H gate, we will have the result of 1/2. And for this one, that will be H. So this is the basic operation of the tensor product. Okay, the last one is not H. This is a negative H. And then we will have its matrix multiplication: 1, 1, 1, negative 1, 1, 1, 1, negative 1, 1, 1, 1, negative 1, 1, negative 1, negative 1, negative 1, 1. So we will create such kind of matrix to represent the H gate on 2 qubit. And we also know, for example, the initial state will be 0, 0, and we can see that is 1, 0, tensor product 1, 0, and then we will have 1, 0, 0, 0. And if we apply them on the initial state, actually we will see our state will be something like 1/2, and this will be 1, 1, 1, 1 for this result. Okay, so the operation will be similar, but the thing like that for multiple qubit gate, actually we need to do the tensor product between these two gates so that we can obtain the operation, the matrix to manipulate these two qubits. Okay. And one thing I want to mention out is that for different system, actually it will define the most significant qubit and also the least significant qubit. For Qiskit, it using this way to encode such kind of things. And for example, if we load this as A, this as B, we will have the state to be A, B. And sorry, maybe let's do it another way. This is A and this is B. We will have the state of BA for the Qiskit if we want to encode it to 2 qubit. And for this one, For the general cases, like what we see for the wiki gates, actually it will use such kind of way to encode to represent the multiple qubits. So this is one thing I want to mention out, because sometimes if you see there is some inconsistent between the matrix multiplication and what the result from the Qiskit, it may mainly because such kind of thing. You want to do the encoding, the tensor product using this sequence instead of the normal sequence from the top to down. Okay, we have already said something about the operation on multiple qubit, and also the next one is that we want to introduce a 2-qubit gate. For example, now we have the Tolliver gate or the C0 gate, and oh no, this is not C0. This is control X gate, and so the matrix multiplication of this stuff will be a 4x4 matrix, and we will have the, for example, using in the following of this presentation, actually we will use such kind of sequence for the introduction, and for such kind of encoding, actually we will have this stuff to be the control X gate. So we will have the matrix multiplication between that is 1 1 and 1 1, and I is identical matrix that is 1 1, like this one. And so we can see something behind this. So if we have, so the meaning of such kind of gate is that if the first qubit has a state of 1, we will do X gate on the second state on the second qubit. So this is logic behind, this is the logic behind such kind of 2-qubit system. And if we write down the matrix multiplication, we can see the first one is 0 1, and the second one the state is 1 0, and we use this sequence for the encoding, and we will have our stuff like the 0 times 1 0 and 1 times 1 0. After this, we will have 0 0 and 1 0. And when we do the operation on using this gate, we will get our result. Then will be this will be 0, this will be 0, this will be 0, and this will be 1. So what's thing behind this? We already see. So for this control X gate, if it is 1, it will flip the second one, so it will be 1 and this after the operation, and the first one will remain the same. So after this, actually we want to have such kind of state, right? And this is what we do using the matrix multiplication. So if we want to write out this using our tensor product, we can evaluate whether it is correct or not. So we have 0 1 tensor product 0 1, and we can see we have 0 0, and the second one is 0 1. So using the tensor product, actually we have exactly the same result like what we do using the operator. So this is the control X gate. It will help us to control the first using the first qubit to control the second qubit. And the first qubit is not need to be one state. It can be other state, like if we use a H gate here, and so this will be our next one. So this will be our entanglement. So if we have the Hadamard gate and the first qubit, and then we will apply a control X gate, actually we will help this 2 qubit to enter a superposition. So to enter the entanglement. So let's see a little math behind this, and I think we can move it more faster after this. So for the H gate, actually we will follow the same thing, because we have already know the control X gate is 1 1, and this format. And if we apply a H gate here, actually what we have already seen is that it will help us to enter a superposition that is 1 over square root of 2 and 1 1. And this one is identical stuff. So we can write down the because this is 0 state, so that is 1 0. So then we can write down the state at this position. That will be on 1 and 1 times 1 0 and 1 times 1 0. So this is the state at this place. So after we write compose it to our matrix multiplication, it will be like this way. And what we have is that this will be give us 1, this will be 0, and this one will be 0, and this one will be 1. So for the previous one, you can see that actually we can, the 2 qubits are still independent after we do such kind of operation, like what we do after the control X gate. We can write down, so this is one state and this is one state, so that they are independent and we can use tensor product to obtain the correct result. But now, actually, after we do such kind of thing, actually, the 2 qubits are not independent. Furthermore, let's say this state is 0 0, this is 0 1, this is 1 0, this is 1 1. It represents, you can see, if we measurement the first qubit, the result will be 1. There is a 100% probability that the first qubit will also get the result of 1. So they are coupled with each other now. They are no longer to be independent. For our previous result, we can see 0 0 0 1 1 0 and 1 1. You can see that the 2 qubits actually are still decoupled with each other. So if we measurement this one, and it will not affect the second one. But for now, if you do the measurement on one state, and we can infer what is the state of the second qubit. So this is called entanglement, and also this is why they write down the 0 0 plus 1 1 here. Okay, so this is the very basic stuff on the entanglement. And do you have any question at this point? I believe we have already gone through the fundamental stuff. I know it is very long story and also very details, but I believe this will be very good for us to understand, to better understand what we will have to discuss on the quantum flow. So any questions so far? Okay, if there are no questions, maybe we can move on to the second part, the brief introduction to machine learning. And so the first question is what is a machine learning? Actually, you know that we have different learning approach, like the supervised learning, unsupervised learning, and also the reinforcement learning. So for the supervised learning, the basic idea is that we have a training set, and we are given the label of data in the training data set. And for example, we have such kind of input, X as a image from the minutes, and then we have the label of 3. So we will want to get obtain a function f, so that when we give the input X to the function, and then we can obtain the result of 3. And this is in our training procedure. We want to train such kind of function. We want to find a function f. And in our inference phase, actually we are given some unseen data, like this data. It is not seen for the training, and it does not have label, and we want to use such kind of function to inference, to do the inference and obtain the result of 3. And so this is what we see in the supervised learning. And for the quantum flow, actually we will focus on the inference of the neural network. And here we list some basic mathematics here. So this is we formulate the forward propagation, and we have the loss function. We can define the loss function as the function minus label, so then we can we want to minimize such kind of loss. And for the perceptron, actually, we will have the input X and the bias B, and we will train the parameter theta, so that we can build up such kind of network. And if we tune the value of theta, actually we will represent the function f. And a feed-forward neural network will follow such kind of definition. We do the linear operation first and a bias, and then we do the nonlinear function on it, so that we can obtain our output of one layer. And we will pass the output of the first layer to the as the input of the second layer, so on and so forth. We will have our final result and obtain our finally we can do some classification on the output to tell whether this figure is 3 or 6 or 7. So this is the basic stuff on the neural network. And here, actually, we figure out the structure of such kind of learning. Actually, we are given n, for example, here we given n input. This will be n minus 1. And what we do is that we will build the connection between the input and our weight, the theta, and also bias, and then we can calculate that such kind of thing. And if we want to extend it to multi-layer perception, for example, a deep neural network, when we want to extend it, actually we will add more layers in such kind of neural network, and we will have different weights. So the basic thing is that for the QuantumFlow, what we will do is that we want to accelerate such kind of neural network on the quantum computer. And so now we have enough thing on the quantum side and also the machine learning stuff. The next one is that we want to briefly introduce something about the quantum machine learning. And now let's see some motivation why we want to do the quantum machine learning. The first thing is that the imbalance demand and the supply of neural network on the classic computing. And also you have already seen that the IBM provides such kind of strong quantum computer, and we also expect that we can have more powerful quantum computer with more qubit. So the power of quantum computing is growing. And the last thing is that you can see we have got a lot of details on mathematics on the quantum operation, and you can see the linear algebra is the core of quantum computing. And we also know that such kind of thing is also the core for the machine learning. So that they have natural connection between quantum computing and also the neural network, the machine learning. And so the first thing is that the imbalance between the neural network size and also the classic computing power. And so in this figure, the x-axis represents the error, and the y-axis represents the number of parameters. With a demand of low errors, we can see that the size of neural network grows exponentially. On the other hand, for the hardware, classic hardware, due to the end of the Moore's law, actually we can see the computation power almost, the increase of the computation power almost stops. So there creates such kind of computation gap. The similar thing will existing on the storage. So we have also the storage gap. And we have already seen the slides before. Today we have the 65 qubit, and we will have more qubit in the quantum computer in the coming years. So then the quantum computer will provide a more powerful computing platform to operate such kind of task. And the third one is the linear algebra is the central for both the quantum computing and the machine learning. And you can see for such kind of operation, so this is basically can be seen regarded as one neuron, right? So this is our weight and this is our input. So this is a layer of neuron, and if this is also the weight, so then we can construct the. So this will we have 4 input C0 to C11, and for this one it is one weight, it is corresponding to one neuron, and the second one will be corresponding to the second neuron. So it is very beautiful. So for such kind of thing on the classic computing, we need the number of multiplication will be m by m, and the accumulation is also the level of m by m. But on the quantum computing, if you still remember, so this one is just the 2H gate that we created. So we have 2H gate, and this is just our initial quantum state that is composed of our qubits. And if we can represent we can just use 2 qubits to represent such kind of 4 states, right? And we have this one is just a 2H gate, H tensor product H. And if we apply such kind of thing on our quantum circuit, actually, we can say we just need to use 2 qubits and 2 gate. So this is for the initialization. So maybe 4 gate. So the constant number of gate to implement such kind of things. And we know that the number of qubits will be so here if the input is m, and then we know that the number of qubits will be log m, and so the number of gate will be the same level of such kind of thing, so that we can see we can dramatically reduce the number of multiplication, the number of operators that we to be used for the quantum circuit. So this is the basic idea that the quantum circuit, the quantum computing has the potential to do the machine learning task much better. And in order to do such kind of thing, you have already seen the first step that we need to encode the data to the quantum computer, right? So that the very important thing is that we want to we want to see the how can we encode the data to the quantum computer. And we have one question from the chat, seems this kind of ternary neural network. So yes, so actually we will go through different neural network later, so that you can see whether we can only work on the binary or ternary neural network or other neural network. And as we see that the first step is that we need to encode the data from the classic computing to the quantum computing. So the data encoding will be very important. And here we typically there are 3 types of encoding method. The first one is that we want to ask whether we can encode arbitrary number to a quantum computer. The result is yes. Actually, if we regard each qubit as a binary number, and if we just do such kind of X gate on the last 2 qubits, and we interpret it using this way, we can represent the number 12. And if we add a point here, and we can encode the data 1.5. So we can encode the arbitrary number to the quantum computer. But this is not efficient, because you know that we use too many qubits to represent one number. And this one is called the 1-to-n mapping, and it is used to implement a lot of Boolean functions. And I think this also answered the previous question, that actually if we not only do the computation using the binary stuff, actually we can build up such kind of real number on qubits, but it will have a high cost. And the second thing is that we want to take use of the superposition of qubits to encode the data. So whether we can do this, the answer is yes. Actually, if we rotate the qubit a little bit, so that we can encode, for example, if we want to encode 0.5 to our first state, okay, or to the 1 state, actually we can do such kind of thing. If we rotate a proper angle, actually we can encode this one will be something like 1 minus 0.75 square root. So if we want to encode the data to the probability of the second state, actually we can do it. And now we only use 1 qubit to represent one number instead of using n qubit to represent one number. And this is also known as 1-to-1 mapping or the angle encoding. And the limitation of such kind of approach is that the data, because it is represent a probability, so the data need to be in the range of 0 and 1. And the complexity to represent the one data is the same as the classical computing. And so the third approach to encode data is that we want to see whether we can use the entanglement of qubits to encode data. So that the meaning is that in the second example, we encode the data to the amplitude, to the probability of one state, right? And for the first one, actually, we create such kind of thing to encode the data to just the one state. And the last thing is that whether we can encode the data to the amplitude of the all states. Like if we have 2 qubits, we want to encode the data four data to these qubits. So whether we can encode our data, for example, A0, A1, A2, and A3 to all of these states, actually the answer is yes. Actually, in this case, if we use that kind of gate, actually we can encode these numbers to all of these states. So this encoding is also known as N to log N mapping, and this is also known as amplitude encoding. So the benefit of this is obvious. Actually, we can have a more dense information on the quantum qubits. And the limitation of this is also very obvious. For example, because we know each of the amplitude is corresponding to the probability. So it requires the square of all of this amplitude to be 1, so that we can follow the quantum physics. So this has some limitations on the data. And also it may have some, because for the first 2 methods, actually, we just need to use 1 gate to encode the data. But for now, we need more gates to encode the data. So it may incur higher cost on the encoding phase. So in summary, we have different encoding methods. And the first one is 1-to-n encoding. And for the data limitation, actually, there is almost no data limitations. But the thing like that, it will use all the n number of qubits to encode one data, so it is not efficient. And for the 1-to-1 mapping, actually they have same it will use 1 qubit to represent one data, but the limitation is that for the data it should be between the range of 0 and 1. And for the last one, actually we can see that we can significantly reduce the number of qubits to represent the data, but we have more constraint on the data. We need the data follows such kind of constraint. And also it has a more higher complexity for encoding data. So I think this is a simple overview of different data encoding method. And for the algorithm design, actually they were based on different data encoding method. And in the following, I will go through different algorithms and to see what we have for now and the state of art, what we have for the quantum machine learning. And also we will show why there is some potential that we can achieve quantum advantage. And the very first algorithm is HHL algorithm. And in order to understand this, I will first introduce 2 components. The first one is called the quantum Fourier transform. And this one, the idea is similar to the classic stuff. It wants to encode the binary number represented by the state to the phase. So it follows the 1-to-n mapping. Like the first one, it has some binary number for the qubit, and then we want to encode the stuff onto the phase of our qubits. And here I give an example. So the A state will be a binary like the 0001, or in our case, actually we have 2 qubits, so it is something like the 0-1. And we want to encode such kind of 0-1, such kind of information to our phase in the qubits. And so the QFT actually help us to do such kind of thing. And after we apply the QFT, it will change the phase of our qubits, the change of our amplitude. And then we can obtain such kind of the connection between the QFT times A and also the result. So basically the QFT will help us to encode the binary number to the state of phase. Another on the upside stuff, actually we have the phase estimation. The thing like that, the why we need such kind of thing that the you know that if we have different quantum state but with different phase, actually if we do the measurement, for example the z base measurement, actually we will have the same probability. So if we want to know the difference between these two quantum system, actually we need to understand the phase. So we want to do the phase estimation. And the thing we use here is that if we are given a unitary operator U, and then we want to extract the phase after we for the U, actually we can follow such kind of circuit design, apply multiple control U here, and then we do reverse the QFT, and we can extract the phase to the qubit. So the output of such kind of qubit will also be 1-to-n encoding. And here I give an example. So if we are given the T as our U operator, and we know the matrix representation of T like this way, and so after this we will have the phase inside of our qubit, our one state qubit, the one state of our qubit. And so we know that for our input, actually we want to extract the phase phi, which is defined in this format. And when we do the simple math on this two, we can see our theta will be 1/8. So we applied this circuit to for the T. Actually, we create such kind of circuit, and then we can see the result will be 0, 0, 1, and we have the pointer here, so then we can see the final result will be 1/8. So that is the same with the theta here. So we can extract the phase from operated by this gate to our qubit. So this is a basic idea of QPE, quantum phase estimation. By using the QFT and the QPE, actually the HHL algorithm was proposed. So the problem to be solved is that we are given a matrix A and a vector B. What we want to do is that we want to find the vector X so that it can follow such kind of equation, AX equal to B. So we are given A and B. We want to resolve the result of X. So this is a very fundamental mathematical problem. And why we want to do this is because on the classic computer, it requires the complexity of n kappa to for the computation. But for the quantum, whether we can reduce the complexity to log n kappa square. Actually, this is possible, and this also demonstrates the potential quantum advantage can be achieved for such kind of linear equation. And this will be the fundamental of a lot of machine learning algorithms. So this will so I would like to introduce it here. And now we have such kind of background, and then the next one is that we want to see a lot of quantum neural network. The first one is called the variation classifier, and it can apply different encoding approach to the classifier. Actually, we have a UX here. It can help us to encode the data to the quantum circuit. After that, we will have, we call it as a variation classifier because we use the variation quantum gate, like the what we have already said, the U gate, or the rotation gate, right? The Rx, Ry, and Rz, we have already seen it in our previous fundamental stuff. And after that, we have the parameter of this gate. For example, in the Rx gate, we will have a theta. Ry, Rz all have a theta. So we can integrate such kind of gate in the quantum circuit. And then we can change the theta so that it can be regarded as what we have for the machine learning model, like the weight in our machine learning model. So in this way, if we can tune this theta in a better way so that it can represent one function. And after so we will operate such kind of function on our input data. And after at the end of the circuit, we do the measurement, and then we can extract the result. So this is a basic idea for the variation classifier, the design of variation classifier. And here I demonstrate different quantum circuit for such kind of variation circuit. And you can see we use the Rx gate, RZ gate, and also the RY gate in RY gate in the variation quantum circuit. And so such kind of design is designed based on our neural network. So they have this is motivated by such kind of design. We can have multiple layers, and also we have different parameters in the circuit, but they are not equivalent because the variation quantum circuit or the VQC, the weights in such kind of circuit is highly has high coloration, so that it is really hard to be represented by the classic computer. Another thing, another very big challenge is that the non-linearity is really difficult to be integrated in such kind of circuit, because the quantum circuit, as we have already seen, all of stuff is the multiplication between matrix and a vector. So when we construct the matrix, actually all thing in such kind of thing is a linear algebra. So it is really hard for us to integrate the nonlinear between layers. So this is some limitation and also the property of the variation quantum circuit, the VQC stuff. And on the other side, on the other direction, that is the quantum-based neural network accelerator. Actually, we can design the quantum circuit to accelerate our neural network. So this is similar to the idea of what we have on our classical computing platform, like FPGA, like ASIC, like computing in memory architectures. Actually, we want to design exactly the same function on the quantum circuit, but if we can achieve some speed up, that will be fantastic, so that we can accelerate our neural network on the quantum computer. So now let's see different implementation and to see whether they can achieve quantum advantage, whether they have the potential to achieve quantum advantage. So let's first see the computing using the binary Boolean function. But before that, we want to clarify something about the complexity. So as you see on our classic computing, we have the time complexity that represent how many times that we need to calculate such kind of neural network, right? And for example, the time for this complexity will be order n, because if we only have one meg, if we only have one multiplication and accumulation circuit, actually we need to do the weight multiply the input for one pair and one time. So the time complexity for such kind of scenario will be order of n. And so the space complexity, because we only have one meg and we only need one space to store such kind of temporal result. So the space complexity will be order of 1. So the time and the space complexity will be order of n. So if we have n meg, so that means we can do the computation in parallel. In this time, we only need the time for order of 1, because we can calculate all of this weight and input in a same time. And but the space complexity will be order of n, because we need such kind of n space to store the result and also to compute this stuff. So we can see similar, the time space complexity will also be order n. So this will help us to have a fair comparison if we want to compare the classic computer and the quantum computer. So if we only consider the time complexity, we can see our classic computer, it can be order of n, and it can also be order of 1. So which one we need to use for the comparison for the classic and the quantum? This is not clear, right? But because this one do not consider parallelism, this one consider parallelism. So in order to have a fair comparison between the classic and the quantum, actually what we want to see is that we want to use the time and the space complexity. So in the quantum stuff, actually we can also see that for the circular design, we have the number of qubit, the number of gates to be placed on the quantum circuit. So we can have such kind of circular length. And also we can have the number of qubits to be used to do such kind of computation. So this is a quantum circuit, and we can regard the circuit length as a time complexity, because for each gate or each pair of gate, actually they will run using one single cycle on the quantum computer. So we can use the circuit length to represent the time complexity. And for the space, actually, for the number of qubits, actually, it is also related to the number of storage that we have for the classic. So for the space, we use a qubit. So for the time space complexity, we will use qubits times the circular length. And assume that so this is all what we have for the a neural computation, and we know that for the classic computer the complexity is order of n. So if we want to achieve quantum advantage, so what is the quantum advantage? Quantum advantage means that if we can reduce the complexity exponentially, like in this case, if we can reduce the complexity from order of n to order of polynomial log n, so we can achieve such kind of such kind of exponential speed up, right? So this one is our goal. We want to achieve quantum advantage, and we want to obtain the exponential speed up. By the way, the polynomial log n is something like log n square or log n cube. So this stuff is called the polynomial n. So if we can achieve such kind of complexity on the quantum computer, actually we can achieve quantum advantage compared with the classic computer. So we explained something about the quantum advantage here. And next, we were going to see whether the existing design can achieve such kind of quantum advantage. And they were based on different data encoding. The first one is based on the Boolean function that use a 1 to n encoding. And the thing like that, we are given a quantum state. The first group of state represent our input x, and the second state represent our output. And we want to do such kind of transformation from the x0 to xfx. And the f will be the function that we want to implement in the neural network. For example, if we want to realize a nonlinear function like the ReLU, we want to integrate the f here. So fundamentally, for the Boolean function, what we can do is that we want to have a function f, and we want to transit our state from x, y to x and y to do the exclusive OR on the fx. And so here is what we want to have on our quantum circuit design. We want a unitary matrix UF, so that it can keep our input as the same, but it can change our output and integrate the function fx into such kind of result. And if we consider the ReLU, and we can see that what we want is that we want to do the ReLU on our input x. And so how can we design such kind of circuit? It will depend on such kind of truth table. And we can see that if we assume the first line as our sign of a number, and the second qubit will be our input data, I mean the real number. Actually, what we can see is that we know the ReLU function is something like the this one. If it is less than 0, it will be 0, and larger than 0, it will be the original value, right? So for this case, we know that for this two stuff that will be positive, and it will remain the same value as what we have. So for 0, 1, it will remain 1, and for 0, 0, it will be remain 0. And for the negative number, like if the sign is 1, it represents the negative number. Both of them should be the output of ReLU will be 0. So we have such kind of the function for the ReLU, and so we can observe that the thing like if we have the 0 and 1, so we can use the x to be our control end. And if it is 0 and 1, like the circle here represent if the state is 0, it will trigger such kind of event. And this one represent if the state is 1, it will trigger this this event. So in this case, actually, we will have our third qubit as our output qubit. And if we apply such kind of gates, so it means when it is zero, when the input is 0, 1 state, it will trigger the output qubit to apply a X gate on the output qubit, so that it will flip the output qubit only when the input will be 0, 1, and we see the output is 0. So in this case, when we apply such kind of gate, only the input is 0, 1, it will flip the state of our output qubit. So we can implement such kind of ReLU function in such using such kind of gate, just one gate to implement this. So if we have more numbers, higher precision, actually we can follow the same idea to design the quantum circuit. So this is our apply the Boolean function to realize the nonlinearity or other functions on our qubit. So here is that it can also use the QPE to do such kind of thing, to extract the output, and then it will pass it to a unitary gate to implement some nonlinear functions. And now let's say some complex some issue on the complexity. We know our goal is that if we have n qubit, if we have order of n time complexity on the classic computer, we want to achieve polynomial log n on the quantum stuff. But we can see for the number of qubit here, it includes the n, and the number of gates include n. This is for the first implementation. And we can say, so for this stuff, it easily cannot achieve quantum advantage because the complexity is at least n squared. Similar thing, if we use such kind of the amplitude encoding for our input, actually the thing like that, the number of qubit can be minimized, but the number of gate complexity also requires n squared to conduct the computation. So this design also cannot achieve quantum advantage. The similar thing is the implementation in this paper. Actually, we also have the n the term n the term n in our number of qubit. So it simply prohibits us to achieve quantum advantage. So using such kind of Boolean function 1-to-n mapping, actually it is really hard for us to achieve quantum advantage. Another thing is that if whether we can use a 1-to-1 mapping to implement the neural network, the answer is also yes. So the problem here is that if we are given the input and also the weight and also a bias, we want to implement such kind of function. So this is the basic neural operation, right? And for the quantum stuff, we are given different probability, and also if the bias and the weight can be integrated into our rotation gate, like RY gate, and we want our output theta to be integrated in our angle. So basically, it will apply the control RY gate to accumulate this angle on 1 qubit. So after such kind of operation on all of qubits, actually it can help us to do the accumulation. So in this case, we can integrate our desired output in the angle of the RY gate. So this is a basic idea of how can we do the quantum neural using such kind of 1-to-1 mapping. The basic idea is that it will use their input will be the binary number. It will be either 1 or 0. If it is 1, it will do the rotation on an auxiliary qubit, and the weight is integrated in the angle. And so the output qubit will turn a certain angle from the 0 to 1 angle. And after that, if we have the second qubit, it is also one, it will continue to turn some angle. So we can accumulate such kind of angle in our auxiliary qubit, a qubit, and then we can do such kind of add operation. And also the multiplication is it can be integrated in such kind of control gate. So in this case, actually, we can realize the MAC operation on our neural network. They have exactly the same function. Okay, so the next one is that in such kind of design, if we want to integrate the non-linearity, how can we integrate? So the previous this paper also provide an approach to implement the arctangenting function into the quantum circuit. The basic idea they will use the repeat until success to integrate such kind of thing. There are a lot of details, but our focus is on the complexity. And we can see for the linear operation, actually it requires n qubit to encode the data, right? So for each data, we will encode it to 1 qubit. So the complexity for the number of qubit will be order of n. And also we can see for each operation, for each pair of each pair of input and weight, actually we need one gate to implement it. And all of them are operate on a last gate. So they cannot do the operation in parallel. They will sequentially do such kind of thing. And we know there are n qubit, there are n input, and it will require n such kind of gate to rotate our output qubit. So the complexity for our gate is also order of n. So in this case, our time and space complexity will be order of n squared. And similar for the non-linearity, it also requires such kind of complexity include n here. So using such kind of implementation, it is also very, very hard for us to achieve a quantum advantage. And so in the last thing, we are focused on the amplitude encoding, because we know that for the first two approach, the encoding itself requires a lot of qubits to represent the data. It prevents us to achieve quantum advantage. And if we apply the amplitude encoding, we can encode n data to log of n qubit. So it provides that kind of potential. But let's say a little details, whether there exists some problem and also whether we can really achieve such kind of quantum advantage. Okay, so here we give, we again give a quantum neuron. We need to do the summation of the qubits. And we have some assumption in this place. We are trying to use the amplitude. And the very simple one is that we have already seen, if we apply the Z gate, we can change the sign of our amplitude. So whether we can do it for the binary neural network, I think this is the very first trials on the quantum neural network using the amplitude. And so this is very straightforward because we can change the sign of our qubit, our amplitude. So the thing is that we want to change the sign of all of the sign according to the weights, and then we can implement such kind of function. For example, if we are given such kind of input, we already know it can be encoded as 2H gate in the previous examples. And if we want to change a sign of this, so if we can apply such kind of control Z gate, it will flip the sign of the last amplitude. In this case, actually, we can implement the same function as we do on the classic computer. But the limitation here is that by using the control Z gate, we can only integrate the binary weight. So we will integrate the binary weight. We will implement such kind of binary neural network instead of a universal neural network, or with such kind of approach. So similar with a variation quantum circuit, actually, instead of directly extract the output at the end, actually, what we do is that we have a UW that is corresponding to our circuit design corresponding to the given weights. And after that, we will do some extraction of our result using the control X gate on a new state. So this is a whole mapping from the neural network, the classic neural to a quantum neural. Here, this one will be our output. That will be corresponding to our output. And this one, as we see, that is something like the control Z gate that will be our do our summation function and also the weight embedding. And at the end, we will do some nonlinear function and also extract the output to our output qubit. And this one will be our encoding of our input. So we can separate such kind of circuit into different parts, and we can investigate the complexity of each part to see whether we have the potential to achieve quantum advantage. Okay, so we can see for such kind of thing, the number of qubits will be order of log n, right? So this is perfect. We can reduce it from order n on the classic one to the order of log n on the quantum stuff. So the next question is about the circular length. Whether we can control the circular length to still follow the order of polynomial n. So this will be our big challenge. So for UX, actually we see the number of qubit has already been controlled. For UW, it also work on the same qubit. So the number of qubit will be no issue. Also for the output, we only need 1 qubit. And now we need to consider how many gates that we need to apply so that we can achieve such kind of function. And for the for the last one, for the output extraction, actually we only need the log n to operate. For example, if we want to extract it from such kind of gate, actually either gate, actually we only need log n for the computation. And so then for the output extraction, that will be no problem. But the challenge here is that how can we design the UW? How can we embed the weight to the quantum circuit? And how can we embed the input to the quantum circuit? And this one is known as the quantum state preparation. A lot of study are focused on this area. And this one is what we want to do. We want to integrate the weight to the quantum circuit. And so anyway, for now, we can see that only the amplitude encoding provides some potential for us to achieve quantum advantage. But how can we achieve such kind of gates, such kind of circuit, so that the number of gates, so that the circuit length can be also remain in the level of log n. So this will be our big challenge, and this is what we will talk in our quantum flow design. Okay, so here is a halfway takeaway. So we have already seen different encoding method like the Boolean for Boolean function, the angle encoding, amplitude encoding, and we also see the variation quantum circuit, which is designed based on the neural network, but it has no classic correspondence for the neural network. And it can the benefit of such kind of thing, the advantage of variation quantum circuit is that it can integrate any real number weights into the circuit and also the real number input. It has very low limitation on the data representation, but the nonlinearity is very difficult to be integrated to such kind of circuit. And as we know, for the deep neural network, if we do not have the nonlinearity, actually the deep neural network will become a one-layer neural network. So it will very harmful for our representation of neural network. So this is some limitation of the variation quantum circuit. And for the quantum-based neural network accelerator, it has more flexibility on the design, but not all design can achieve quantum advantage. We have demonstrated that for the 1-to-n or 1-to-1 encoding, it is really hard for us to achieve quantum advantage because the complexity of the qubits, the data encoding itself is already larger than order of n. So then we can hardly to achieve quantum advantage. So the only hope is on the amplitude-based design. So but there are some uncertainty whether we can design a circuit that can achieve the exponential reduction on the number of gates, so that whether our circular length can be maintained on the order of log n level. So this will be what we will discuss in our quantum flow design. And finally, in this section, actually, I would like to introduce some application. So remember that we have some problem for also for the encoding of data, encoding of the input data, and also do the computation of the weights. So we have these two tasks need to be done, and so let's say some application, they are partially resolve some of this problem. And the first application is the Q gain. And so on the left hand side, we introduce the classic gain, and something like we have a discriminator, and we have some real data to generate for the discriminator, and we have a generator to generate some data. It will based on some noise. So on the quantum side, actually it will change the noise and the generator to the using the quantum circuit. And so it can formulate such kind of quantum circuit to implement the GAN application. So in such kind of circuit, the key part is how can we integrate the parameter, and they use the variation quantum circuit. Why I want to introduce, because there is a very interesting application. They do the quantum state preparation that is related to our first task. How can we integrate the input to the quantum circuit? And they use the GAN to generate the quantum circuit to prepare the quantum state. What they do is that they will train using the training data and create such kind of discriminator, and also the generator will help us to generate the quantum circuit, so that the quantum circuit can have the same the output of our generator will be regarded as the same stuff as what we have for our training data. So using such kind of approach, the generator will help us to generate the quantum circuit, and it is potential to generate some quantum circuit with low complexity. So this is what they explore using the quantum GAN. And another application is that the author in this paper to use the quantum GAN to for the drug discovery application, and the replace the first few layers using the variation quantum circuit, so then it can take some advantage of variation quantum circuit in their application. And the quantum RNN is based on our introduced quantum neural design. It will, for example, it will use such kind of control R gate to control rotation gate to accumulate the weight, the output and 1 qubit, and then it designs such a structure to do the recurrent neural network. And finally, we have the ASTM. The author in this paper replace the neural computation. Here, the neural computation of the weight and the input by using the variation quantum circuit, so that we can we can do a quantum version of ASTM. So, and this is the variation quantum circuit that they use in the work. So the takeaway here is that actually the quantum computing can be applied to different applications, as what we see, the drug discovery and for example, the natural language processing using the recurrent neural network or ASTM. And but the most important thing is that we want to achieve quantum advantage, and for the real applications. So we want to do such kind of things. So we have seen some effort on how to efficiently encode the data to the quantum circuit using the GAN. And in the next one, we will present our quantum flow to solve the second problem. How can we do the computation on the quantum circuit to achieve the quantum advantage? So this will be our target for the next session. Okay, I think we can stop here for the first session. Whether you have some questions, maybe we can clarify during this period. And yeah, so any questions from the audience? And maybe I think you can unmute, or you can type in the chat so that we can discuss a little bit. Okay, so if there is no question, maybe we can stop for 10 minutes and then we can come back to continue our second session on our quantum flow. That one will help us to solve the problem. How can we do the computation efficiently on the quantum computer? Okay, great. So in this case, maybe we can say something during our break, and let's show my screen.
Isolated from the rest of the universe is a quantum computer.
So we will come back around 11 o'clock, and here we shoot some fundamental stuff.
Future and has the potential to revolutionize our lives with its turbocharged computation. But quantum computers aren't the next generation of supercomputers. There's something else entirely. And before we can even begin to talk about their potential applications, we need to understand the fundamental physics that drives the theory of quantum computing. We'll need to dive into another dimension, smaller and more alien than anything we intuitively understand, the subatomic world of quantum mechanics. In the 1980s, one of the most important physicists of the 20th century encountered a major roadblock. Richard Feynman was hungry for a window into the quantum universe. But quantum systems, by nature, are fragile, and the information they hold hides from us. Because Feynman couldn't directly observe quantum events, he wanted to design a simulation. It quickly became clear that his computer wasn't up to the task. As he added particles to the quantum systems he was modeling, the cost of computation began to rise exponentially. Feynman concluded that classical computers just can't scale up fast enough to keep pace with the growing complexity of quantum calculations. Then he had a breakthrough. What if he could design a tool made up of quantum elements itself? This instrument would operate according to the laws of quantum physics, making it the perfect way to probe the mysteries of the quantum realm. The idea of the quantum computer was born, and by dreaming it up, Feynman had started to build a bridge between quantum physics and computer science. To understand how quantum computing works, it's essential to start by understanding what makes it quantum in the first place. This means that we need to talk about what's at the heart of quantum physics, a concept called amplitudes.
Quantum mechanics, at its core, is a change to the rules of probability. And this is also where the power of quantum computing comes from these different rules of probability than the ones that we are used to.
For example, if you want to know the classical probability of an event, say a coin landing tails exactly 10 times out of 20, you add up the probabilities of all the different ways that event could happen. That's just common sense. But common sense doesn't govern the quantum universe. Before you measure a subatomic particle, you can think about it as a wave of probability that exists in a kind of black box, a quantum system with many different chances of being in many different places.
Amplitudes are closely related to probabilities, but they're not probabilities. The key difference is, well, probability is always a number from 0 to 1. Amplitudes are complex numbers. And what this means is that they obey different rules. If I want to know the total amplitude for something to happen, I have to add up the amplitudes for all the different ways that it could have happened. But when I add up amplitudes, I see something new, which is that a particle might reach a certain place one way with a positive amplitude and another way with a negative amplitude. And if that happens, then those two amplitudes can cancel each other out so that the total amplitude would be 0. And that would mean that that thing would never happen at all. This is sort of the central thing that quantum mechanics says about the world, right? That the way that you describe a physical system is by a list of amplitudes. And the way that a physical system changes over time is by a linear transformation of these amplitudes.
But how can quantum computers use amplitudes to store and manipulate information quantumly? This is a qubit. It's the basic computational unit in quantum computing. Qubits are like bits in a classical computer, but with a crucial difference. A bit is binary. It stores information in strings of binary digits that can only be 0 or 1. But qubits are made of subatomic particles, so they operate according to subatomic logic. Qubits can be 0, 1, or what we call a linear combination of 0 and 1. This fluid combination of amplitudes is at the core of quantum computing. Before you measure a qubit, it exists in a state called superposition. You can think about it as a quantum version of a probability distribution, where each qubit has some amplitude for being 0 and some amplitude for being 1. Superposition is the reason why it takes a vast number of classical bits to describe the quantum state of even a tiny number of particles. When two or more qubits are in this closed state of superposition, they relate to one another through the phenomenon of entanglement. This means that their final outcomes, when we measure them, are mathematically related.
The key concept for understanding how quantum computing can be powerful compared to classical computing is what we call quantum entanglement. And that is the word we use for the characteristic correlations among parts of a quantum system, which are different from the correlations that we normally encounter in the classical world in ordinary experience. You could think of it as like a book. When you look at the pages one at a time, you don't see any information, you just see random gibberish. It's because the information isn't encoded in the individual pages, but in the correlations among them. And to read the book, you have to collectively observe many pages at once. It turns out, and this is part of what's so interesting, that if you want to describe very highly entangled states using ordinary bits, it's extremely expensive.
Imagine that you had a primitive 10-qubit computer. It could store 2 to the 10th power values in parallel. To describe this entangled configuration with a classical computer, you'd need 2 kilobytes or 16,000 bits. Expand to a system with 500 entangled qubits, and you now require more classical bits than there are atoms in the known universe. This is exactly what Feynman meant when he said that classical computers weren't scalable for simulating quantum mechanics. For a quantum computer to be of any use, you need to measure information from the qubits to get an output. The problem is, when a quantum system is measured, it collapses into a classical state.
If anything carries away information about whether that qubit is 0 or 1, so for example, if that information gets reported in some radiation that's escaping from the quantum computer, then the effect on the qubit will be exactly as if someone had measured it.
To extract an answer from the quantum system that isn't just a random outcome of probability, like the flip of a coin, we have to use interference.
Interference when waves in a pool hit each other, and one wave is above the surface and the other wave is below the surface, and they hit each other and they cancel each other.
Interference is just what amplitudes do when you add them up. If something can happen one way with an amplitude of 1/2 and another way with an amplitude of -1/2, then the total amplitude for it to happen would be 0. This is what you do in the famous double slit experiment. You close one of the paths, and then you see that now the thing that previously never happened now can happen.
This is a quantum algorithm. Scientists can harness interference by creating a deterministic sequence of qubit gates. These qubit gates cause the amplitudes to add up constructively. This means that they're mathematically guaranteed to boost the probability of seeing one of the right answers.
You might ask, how could you possibly concentrate all this amplitude on the right answer when you yourself don't know in advance which answer is the right one? This is exactly why designing quantum algorithms is so difficult, and why we have a whole field that's been studying it for decades.
Since 1994, there have been a few major breakthroughs in quantum algorithms, with theoretical applications in fields such as cybersecurity and search optimization. But according to most experts in the field, quantum computers are most likely to be useful for what they were born to do, when a curious physicist wondered about the deep structure of our world.
I find quantum computing exciting as a way to explore physics, Now, whether that's going to make anybody any money, whether there will be practical applications in the near term, that's still very much an open question. But at least for physicists, it's an exciting time.
The truth is, the most important application, I believe, of quantum computers is something that we don't know yet. I'm sure that once we have a quantum computer to play with, we will find amazing applications that we can't yet foresee.
Okay, great. Maybe we can come back and continue our second session. Yes, actually, as you see from the video, actually we have already seen that so it is very important that we can operate on the amplitude and also the thing like that if we want to design a quantum algorithm, actually we need to design a quantum circuit. And also you see that what will be the kernel application of the quantum computing. It is still an open question. So this is also a very strong reason that we want to explore the potential of the accelerating the neural network on the quantum circuit. And if we can achieve such kind of quantum advantage, that will be a big motivation for us to do the neural network. And because for neural network, actually it has a wide range of application, so that it is really fantastic if we can have such kind of quantum advantage. So in the second session, we will see the design of QuantumFlow and demonstrate a lot of hands-on example to show how can we use the QuantumFlow and how the QuantumFlow works. And remember that our goal in the previous slides is that we want to design the UW, that is to compute, to embed the weights into the quantum circuit and to compute the neural, the classic neural, the neural operation in an efficient way. So we are targeted on this. We are targeted on this stuff. Whether we can reduce the quantum circuit length for embedding the weights into the quantum circuit. And so in this session, actually, we will have three goals. The first goal is that we want to correctly implement the weights, the computation between weights and input to the quantum circuit. And our second goal is that we also want to implement some non-linear function in the quantum circuit and extract the output via the quantum using the quantum circuit. And our second goal will be efficiently implement the neural computation to the quantum circuit, so that we can reduce the complexity from order of n to something like order of polynomial log n for the computation. So this will be our second goal. And our last goal is that we want to scale the system up, whether we can not only focus on one neural computation, but we can also do the stuff on the multi-layer perception, so that we can, at the end of the day, we can implement a deep neural network. So as what we have already seen, even we want to focus on the quantum implementation for the neural computation, but the very first step is that we still need to do the data preparation. One thing I want to point out here is that for the data preparation, actually there are a lot of work done the research on this field, so that our objective is not to optimize the data state preparation. Instead, we want just to see how can we encode the data to the quantum circuit, so that it can support our exploration on the quantum circuit design for the computation. So in order to design the accelerator on the quantum computer, let's first review the design of accelerator on the classical hardware. So if we are given a circuit, when we want to design it onto the FPGA or the the CPU stuff. So what steps that we are going to follow? So the first step will be the data pre-processing. We need to pre-process our data a little bit, so then it can easy for us to extract some feature. And the second one is the hardware accelerator. So this step is similar to what we need to do for the quantum accelerator. We need to design the quantum circuit instead of the classic circuit. And last, we will do the post-processing to finalize our data and to do some analyze like the classification. So instead of the classic GPU, CPU, and FPGA accelerators, now we want to add the quantum computer, the quantum accelerator in such kind of stack. So let's see the design of the quantum circuit for the such kind of neural computation. So as I already see that for the classic design, actually we will go through 3 steps: the data pre-processing, the hardware acceleration, and the data post-processing. And for the quantum stuff, we will follow the similar thing, but the difference is that we will need some quantum circuit design. But the thing here is that for the classic, the interface will be classic to classic. But here for quantum, we need to do something like the encoding data from the classic world to the quantum world. So this will be some slight difference. So according to such kind of difference, actually we need an additional step, that is quantum state preparation. We need to convert the data from the classical world to the quantum world. Similarly, at the end of the circuit, we need to extract the result from the quantum circuit to the classical world. So that we need some measurement. And at the middle term of the design, we need the design the quantum neural computation. So that is similar as something known as adder tree in our classic design. So this is our unitary design for quantum stuff, and that is corresponding to the design for the classic computer. So in this, from this sense, actually we can formulate such kind of 5-step design for the quantum accelerator for the neural network. And as we already discussed, the first 2 data encoding methods can prevent us to achieve quantum advantage. Therefore, in our work, actually we focus on the amplitude encoding. So let's first say the data pre-processing. Even for encoding data to quantum, actually we know that because we use the amplitude encoding, it has some constraints on the data. So as we have already seen in our first session, the first encoding has very low limitation on the data. The second one requires the data to be in a range between 0 and 1. But for the amplitude encoding, actually it requires the data, the summation of the square of amplitude to be 1. So we have some constraint on the data. So not arbitrary data can be encoded to the quantum circuit. So in this step, in the data pre-processing step, we want to prepare the data that can be encoded to the quantum computer. By the way, because we are, for example, if we are using something like a less number of qubits for the quantum computer, we also need to do some downsampling. For example, if we have only 4 qubits for the data encoding, actually we can only represent the 16 data because we have 2 to the power of 4 amplitudes. So then we can only present 16 data in such kind of 4 qubit system. So we need for an image, like from the image from the Minnesota data set, the original size is 28 by 28. So then we need to do some downsampling to make the data suitable for the quantum system. But if you have a quantum system with more number of qubits, like we have a 64 qubit, there is no need to do such kind of downsampling. Okay. So this will be our first step. We will do some downsampling. And our second step is that we want to formulate a unitary matrix so that such kind of unitary matrix can hold data that can follow the rule of the quantum, that is the summation of the square of the amplitude to be equal to 1. So simply actually we can use some SVD method to do such kind of implementation. So this will be our data preprocessing. So this step can be regarded as a normalization. We need to do some data normalization on the original data so that it can be encoded to the quantum circuit. In our second step, we will do the quantum state preparation. That means we want to take the unitary matrix provided by the data preprocessing, and we want to encode the data to the quantum state. And so this is our task that we want to do. And for the output, we want to verify whether the amplitude state of the quantum system is exactly the same with the data in our unitary matrix, so that we can check whether the data we want in the classical world can be successfully converted to the quantum world. So let's use such kind of 2-qubit system as an example. How can we encode the data? Because we know the initial state will be 0 and 0. All qubit will be in 0 state, so that it will create such kind of vector. Only the first element will be 1. So then if we can encode our data, our normalized data in the first zone of such kind of matrix, actually we can successfully encode the such kind of data to our quantum state. And IBM Qiskit provides such kind of unitary gate so that we can implement the if we have the matrix, we have the data matrix, actually we can use such kind of gate to create a gate, and then we can encode our classical data to the quantum circuit. So here we provide the notebook for to implement such kind of data encoding, and we can see here we first install some library, and then we have some configuration on the data set. For example, the original image is 28. We want to downsampling it to 4x4, and here we define some bench size. And here, because we, for example, in our later example, we will only focus on the classification of 2-digit number, that is 3 and 6 in the minutes data set, so that we do some modification on the data set to extract the label and also the training data. And also we provide the 2 quantum data. We provide the 2 quantum data class so that it can help us to convert the classic data to the quantum data automatically. And then after we build up such kind of, we import the library, then the next step is that we can extract the data from the minutes data set, and we build the train loader and the test loader. And after that, actually we can do some downsampling from the original data to a 4x4 format. And then here is our classic data. So this data cannot be encoded to the quantum circuit because it is violate to the rules for the quantum circuit, to the quantum physics. So that we want for the first step, then we want to do some normalization on the data. And so here we do such kind of normalization, and we can obtain the quantum data using the function provided, by our library, that is 2 quantum data. Actually, here we can see we can obtain the translated vector. So this vector, this data is what we want to encode it into the amplitude of our quantum state. And we can also obtain the matrix that is a unitary matrix, follow the property that is the first line, first column of the matrix to be the data that we want to encode to the quantum circuit. Okay, so here we provide some detail. If you have interest, maybe you can look this into detail. And after that, we can use the the unitary gate provided by the IBM Qiskit, and then we can do some simulation to extract the data to that has been encoded to the quantum circuit. So this is our simulation result, and this one is the value. This one is our simulation result, and this one is the data that we want to be encoded. And we can see by doing such kind of circuit, actually we can successfully encode the classic data to the quantum data. And all of the data preparation is in our first tutorial notebook, and you can check out at this place. Okay, so after we prepare the data, so the second thing that we want to correctly implement the function of the function of neural network to the quantum circuit is that we want to build up the quantum circuit. So we want to see the implementation of our UN layer. So the problem here is that we are given a circuit with encoded input data X, and we are also given the binary weights W. We are also given the W, and what we want to do is that we want to embed the weights into the quantum circuit so that the quantum circuit can perform such kind of function. So this is what we want to achieve in our quantum circuit. And so here we can see, because we are given the trained data, so our focus here is only on the inference phase for the neural computation. We are not talking about the training procedure. So this is our target. And here we have some assumption. So for the weight, as we have already seen, if we can apply the Z gate, actually we can do the multiplication between positive one or negative one to the input easily. So here we study the binary neural network. That means the parameters of weights are binary weights. Then that will be either positive one or negative one. And our second assumption is that the first weight will be always positive one. This is because we will use a quadratic function as our nonlinear function, so that if the first weight is negative one, actually we can flip all weights, so that the result will be the same. And in order to implement such kind of neural computation on the quantum circuit, we can further split our computation into 3 steps. So the first step is that we want to do the multiplication between the input and the weight. And our second step is that we want to do the summation of all the computed partial result. And the third step is that we want to do the quadratic function as our nonlinear function. So in the next, we will see this step one by one. So for the first one, that we want to implement the multiplication between the input data and the weights. And we have already seen that we are given the binary weights, so that some weights will be negative one, some will be positive one. Here, we first use such kind of example to demonstrate, to give you an impression, how can we do such kind of a computation using the quantum circuit. As we already know, for the input, it is a vector, and each of them will associate with one state, right? So we have already know this stuff by using our data preparation step. So the state of the quantum system at this place is demonstrated here. And then we will apply a control Z gate. And we know that for the control Z gate, the matrix the representation is like this way. So this is our Z gate, and this is our identity gate. So this is the matrix representation of the control Z. And what we will do is that we will do the multiplication between our control Z gate, this circuit, and our input state. And after that, we can see that for the output, actually, if we do some simple math, actually, we can see these are all zeros, right? These are all zeros. So then what we can do is that for the first row, multiply the state, it will give us A0. The second one will be A1 and A2 and negative A3. Great. Now we can see that we have already integrated our this kind of weight to the quantum circuit using our simple control Z gate. Okay, so if the position of the weight is switched to another place, whether we can also do such kind of thing, the answer is yes. Actually, what we will have is that we will create such kind of gate. So basically, this means that for the first one, it means that if the first state is 1 and we will flip the second one, so it will operate on the 1-1 state. And here we want to handle the this is 0-1 state. 0-1 state. So then it represents the first when we do the operation. If we apply the same thing like the first one, actually we need to flip the first qubit to be 0, so that we end up flip the NOT gate and on the first qubit. Then we apply the control Z gate. And for such kind of thing, it will help us to create such kind of matrix. So by using all of this gate, it will help us to create such kind of matrix and move the -1 from this position to this position. This can be done by using the X gate. So in the first two steps, actually we do such kind of thing. And for the last X gate, because we do not want to change the state of Q0, so we will recover the state of Q0. So by doing this, actually we can integrate the negative weight to our second state. The similar thing is that for the third state, actually we can also use such kind of circuit by using the control Z gate and the different X gate to integrate the -1 onto the third state. So now we have already seen that for these three states, for these three circuits, actually it can help us to integrate the different weights onto our quantum circuit, right? And we have some simplified notation. So if it is like we use a circle, actually it represents this is we target it is for the state 0, and this is state 1. So we will flip the sign of 0 and 1. If the circuit is on the second place, actually we will flip the 1 and 0. So we use the encoding direction like this way, like this sequence. So after we have we can embed this weight, this weight with one single -1 in the weight. Then if we do the combination of all of this implementation, actually we can encode either weight given by the user to the quantum circuit. So this is a basic idea for the 2 qubit system. Actually, we can use the control Z gate and X gate to encode to embed the weights to the quantum circuit. Okay, so let's say the scalability. So if we have more than 2 qubits, actually, if we have a larger input, so for the 2 qubit, actually, we know that it can represent an input of 4 inputs. And for now, if we have 8 input data, and that are encoded to 3 qubits, whether we can achieve the similar thing, the answer is yes. And the basic gate that we use is similar. We use the control Z gate, and it can be implemented using such kind of basic gate provided by almost all quantum computers. And also, if we change the control end from the solid circle to a circle that represents the control end will be 0. So we can flip the sign of 0, 1, 1 on the quantum circuit. So for using such kind of circuit component, actually we can integrate any arbitrary binary weight given by the user to the quantum circuit for the 3 qubit system. for the 4-qubit system, actually, we can also build up such kind of control Z gate, CCC Z gate, C3 Z gate, and it can flip the sign of or one state. Similarly, actually, we can implement other weights using based on such kind of control Z gate. So now we have done our first part. We can do the multiplication between input and the weight, and then the result will be held on each state in the quantum system. And the next question is that, okay, after we have the output, after we have the result of the multiplication between input and weight, then how can we do the accumulation so that we can accumulate all of this result? So this will relate to our second step. We want to do the accumulation of all of the partial result. So here, the gate that we use is the Hadamard gate, and we will apply Hadamard gate on different qubits. And we know the Hadamard gate has a matrix multiplication like this way. And so if we have multiple Hadamard gate, we will do the tensor product, and the coefficient will be done separately. And here our observation here is that you can observe for the first zone, all of the value will be 1. So if we have multiple Hadamard gate and we do the tensor product on them, the first zone will be always 1, right? And we have an input that is we have already done by our first step. So when we do the mathematics between the Hadamard gate and our input, we can see what we will have on our first state. That will be the summation between of all of this state, because you know that our partial sum is on all of this state, right? So, and our goal is to do the summation of all of this partial sum. So the Hadamard gate, if we place a Hadamard gate using this way, we parallel to execute the Hadamard gate on all qubits. Actually, it will give us the summation of our result, of our partial sum, right? Of our partial result, and give the sum. Another thing is that we want to see the coefficient, because the coefficient here is that we want to do some normalization due to the limitation of the quantum data representation, so that we have some coefficient. And here, for two Hadamard gate, we have two square root of 2, and if we have more, for example, if we have m qubits, actually we will have such kind of coefficient. So this will be exactly the same with what we see in our formulation, and so that we can, after we do such kind of Hadamard gate on our qubits, actually we can calculate our result on our first qubit. And you can see we apply a lot of Hadamard gate, but we can do this in one step because they can compute in parallel. So after we done the accumulation, our third step is that we want to do some non-linearity. We want to integrate the quadratic function on our quantum circuit. And here is our input. We know that the first because we add a new output qubit into the system, and the initial value of output qubit is 0. So we apply such kind of way to encode the data. So only the last qubit is 0, where has some value. For other qubit, if it is 1, the amplitude will be 0. And we are only focused on our first qubit. I mean, on our first qubit state, because our the results are maintained in this state. So we want to extract our result from the amplitude to the probability, so that we can measurement such kind of probability. So this is what we want to do. And during this process, we also want to integrate the quadratic function into such kind of extraction. So we are given such kind of input, and we apply the circuit here to do such kind of extraction and also to do the quadratic function. So after the first 2x gate, we will move our state to the 1 state, because the x gate will change will flip the state 0 0. So it will form the state where the amplitude will obtained from 0 0 0 state to 1 1 0 state. So for 1 1 1 1 0 state, actually we have the amplitude. We will do the same. We will do the same switch of other qubits, other states, and we can obtain such kind of thing. And after that, we will apply a CCX gate on our circuit that represent if the first 2 qubit, both of them are 1, it will flip the last qubit. So the state 1 1 0 will be flipped to 1 1 1. And 1 1 1 will be flipped to 1 1 0. So for other state that will be not be affected. So then in this case, after we apply a CCX gate, we can extract our amplitude, our result. This one is our target to the 1 1 1 state. So now after we have this, actually we can see for our output qubit, you can see now it is on the one for the ones if it is on the 1 state, actually we want to obtain our result here, and you can see only the amplitude of the last state is our result, and other state will be 0. So this means for this one will be 0 0 0 0, and this one will be our result. Okay, so in this case, actually, if we measurement the output qubit, actually it will help us to obtain our result. But our original data is on the amplitude field, so it is something like the square root of x norm on with the summation. But now we translate it to the, when we do the measurement, it will obtain it will naturally automatically add the quadratic function to our result, because the probability is the square of the amplitude. So then we can integrate such kind of square here if we do the measurement. Okay, so here is our circuit design. So in this way, actually we can correctly implement our new our classic neuron onto the quantum circuit. And here in tutorial 2, actually we gave the code to implement such kind of thing. And if we uncommon this stuff, we can add the package, and at this place, actually we are given we do the same thing like the data preparation tutorial in the first tutorial, and here we given the weights, and also we given the weights for the second layer. And okay, so let's further see. So we are given the weight for the first layer. Actually, for this tutorial, we are only focused on the weight for the first layer, and after that we can build up such kind of circuit. So in the Qiskit, actually it will give us a view of circuit using the very fundamental quantum gate instead of CCCZ gate. It will build upon the control X gate, the Tolliver gate, and the control Z gate. But for such kind of this part, actually it is something like the CCCZ gate on our third circuit. Okay, so the thing like that, we are given the weights, and also we are given such kind of design. Actually, we can build up the quantum circuit using this code. And after that, if we do the simulation, actually we for example, we do this amount of shot, actually we can obtain the result for our hidden neuron. And also we can do the thing on the classic side. This one we implement it using the PyTorch, so that we can see the result obtained from our quantum simulation is almost exactly the same with the result obtained by our classic computing. So here we can see that by using this way, actually we can correctly and successfully implement the classic neuron onto the quantum circuit. So if you have any questions, maybe we can stop a little bit at this place and I can make some clarification. Okay, so is there any questions? Okay, if there is no question, maybe we can move on to our code design part. So now we have already seen that we can successfully implement the quantum the neural computation onto the quantum circuit, but the challenge is that we still need to handle how can we do the non-linearity function in a quantum circuit. As we see, this is a big trouble for the variation quantum circuit. So in the QuantumFlow, whether we can implement the non-linear function into the quantum circuit, this is one challenge that we want to address. The second one is that after we know the implementation of one quantum neuron, that is, we know the implementation of one quantum neuron. So how can we scale it up to multiple layers? It seems straightforward because we have already the implementation of one neuron. So we can repeatedly do the one neuron, and then we can formulate such kind of fully connected layer. But the thing like that, if we want to repeatedly use the neural designed before, actually we need to go through the classic computing for analyze our result, and then we will need to we need to further convert the classic data, classic output to the second layer to the quantum computer. So we know that, as you can imagine, that the interface between the quantum and the classic is very costly, right? So this will be another challenge posed for us, whether we can do such kind of multi-layer neural network onto a quantum circuit without going to the measurement. And here we given the complexity comparison between the state preparation and the computation. As you can see, the state preparation can easily dominate the whole complexity. That demonstrates that the cost for the data conversation between quantum and classic is very high. So that what we want to do is that we want a quantum circuit that we can stream the input data into a quantum circuit, and it can follow through the quantum circuit to implement the full neural network, multi-layer perceptual neural network, and then it will output our output at the end of the circuit. So we do not want the classic computing to be involved in such kind of computation. And the third challenge is that by using the previous design, actually we can see that we will, for each weight, actually we will have one quantum gate, one control Z gate to implement one weight, right? So, and in the worst case, actually we will have half of the weight to be the -1, so that the complexity of the previous circuit designed to implement the quantum to implement the neural computation onto the quantum circuit is still order of n. So in this case, if we do not do the circuit optimization, actually we cannot achieve quantum advantage. So we want to reduce the circuit depths so that sorry, here should be order of log n. Okay, so we already know the number of qubits is order of log n. So if we can minimize the circuit length to be also the level of order of log n, actually we can achieve our target. Then the cost can be order of polynomial log n instead of n square or order n that is done on the classic computing. So this will be our third problem need to be addressed. So let's first see how can we implement a feed-forward neural network onto the quantum circuit without going to the measurement. So this for this, we propose such kind of co-design framework that is QuantumFlow. And so here is our some of our observation. So for our first layer, we will encode the input data to the amplitude of the quantum circuit, and the amplitude at the end of the stuff. If we want to have the quadratic function, actually we need to do some translation from the amplitude space to the probability space, so that we can achieve the quadratic function. And so we are thinking about whether we can directly use the quadratic function, the output of the quadratic function as the input of our second layer without going to the measurement. So we can remove the measurement here. So in order to achieve this goal, in order to directly use this data, actually we will further modify our neural network model. So we are no longer able to use a digital number to represent the data. Instead, because it is represented by the probability of one state, actually, so it is associated with a random variable. So the thing like that, we need to we need to have our input to be the random variable, so that such kind of neural network can be mapped to the quantum circuit using the random variable as input. So this is what we do. So we see our what is our output and the first layer, and we want to directly use the output of our first layer to be the input of our second layer, so that we need to do such kind of data format transformation on our classic neural network or on our neural network model, our neural network architecture. So for the encoding of the random variable, actually, so if we want to simulate, we want to study how can we design the quantum circuit to implement a neural, the input is no longer to be digital number, but to be the random variable. Actually, we also need to encode the data to the input. And here we use the angle encoding, that is a one-to-one encoding, and we can regard the number, the input number as a random discrete random variable that has -1 and +1, and we can use such kind of RY gate to encode the data to the quantum circuit. And similar with our previous design philosophy, actually, the thing that we want to design the quantum circuit here, so that it can process our input, which is random variable. So we want to also design the UN for such kind of scenario. So we also propose the random variable version of our data encoding. So it is using the RY to encode the data. And for the neural computation, actually, similar with the previous one, actually we need to implement such kind of implement them using 3 steps. First, to do the multiplication between input and weight, and the second, to do the summation of all of the state, and finally we will do the quadratic function. And here for the input, for the weight encoding, in this case it is much more simple, because for each qubit it represents one data. So then if we want to have a -1, we only need to add a X gate to the quantum circuit, so that it will flip the sign of the it will flip the state of our input. And for the neural computation, actually we use such kind of encoder to implement the neural computation. It will use the control Z gate for different qubits. So by using such kind of circuit, actually after a mathematical analysis, actually we can see that we can obtain this state. So the fundamental idea here is that for the computation, our classic side, we are based on the random variable. Actually, at the end of the computation, at the end of the summation, actually the output will also be random variable, and for the random variable, that the value will be -1, it has some probability, and the +1 it will have some probability. So in our design, we will try to split all of this state, this amplitude, and calculate this correct state. And during our computation, if the value is 0, we know that at the end of the result, we will do the, if we want to do the expectation, actually, we will do the 0 times such kind of probability, right? So in this case, actually, we will do such kind of thing in the implementation of the circuit, so that when we accumulate this result, we will have 0 to represent this probability, and for the 0, state, it will hold the positive the probability for +1, and for the last this state, it will hold the probability for -1. So we will distribute the different value to our state, and we will manipulate this state to achieve this result. And after that, we will similarly use the control the Qiskit and the control Qiskit to extract the result to our output qubit. So we in that paper, we demonstrate that using such kind of design, we can implement the neural computation in the random variable version instead of the classical one, use the real number. And after that, when we have the first layer using the first design, and now we have the random variable weighing for the second layer, actually we can directly connect the neural network without going through the classic computer. And then at the end of the circuit, we will do the measurement, and the output of the first output will be the probability of 3, and the second one will be the probability of 6. For example, if we use Minix 3 and 6 as our test data set. And here we give the implementation of such kind of neural network, and if you run it, and this one will help you to create the neural network with this given gate or this given weights. And finally, if we run the whole program, actually you can see that we are using such kind of approach. Actually, we can do the classification on the quantum circuit. Okay. So maybe let's move to the next part, and maybe that program will run some time. And our third challenge is and the high complexity in the previous design. We want to reduce the complexity to the order of log n or polynomial log n for the computation. And here we again apply the co-design philosophy here to do some changes on the classic neural, so that it can more adapt to the quantum circuit design. Remember that we applied the binary neural network, so the weight are either +1 or -1. So the thing here is that after we obtain the encoded input on the quantum circuit, we need to do the assignment of the -1s to the quantum to the corresponding input. So the first way to do such kind of implementation is what we introduced. We will use such kind of control Z gate to encode one weight to one state and one time. Okay, so for this gate, it will change the sign of one state. For example, if we say this guy, it is 00001, so it will change the state of 00001. And a better implementation is that instead of change the sign of one state and one state at each time, actually we can change a set of state using this control and Z gate, control Z gate, to change a set of state at the same time in parallel. So in this case, we can utilize the high parallelism provided by the quantum computer. But even in this way, actually, as demonstrated in this paper, such kind of implementation can still not reduce the complexity to order of polynomial n. So our observation is that the weight order is not necessary to be fixed. Actually, we can change the order of our weights so that we can still obtain the correct result if we also change the corresponding inputs. And the benefit here is that we are not required to encode the weight to the exact position, but we just need to encode the same amount of negative ones into our quantum circuit. So in the previous example, you can see in the previous two implementation, we need a lot of quantum circuit, a lot of quantum gates. But here, if we want to change we have 6 negative 1 in our weights. Actually, we can only use 2 gates to implement such kind of thing. And the final thing is that for the input, we need to swap their position a little bit so that we can so that we can reduce the number of gates to be used in our quantum circuit. And here, in order to achieve this, actually we propose an algorithm to achieve any weights, any number of negative ones in our weights. So that for any weight, actually we can also apply this algorithm to encode the weight to our quantum circuit. And we demonstrate that using this algorithm, in the worst case, we will use all of this complicated gate once. And the simple version of this composed gate, the cost is listed here. And by some simple calculation, actually we can see that for the input of 2 to the power of k, the number of input to be the 2 to the power of k, actually we can reduce the complexity to the order of k square. That means if we have the input to be order n, the complexity of our implementation will be order of log n square. So in this way, actually we can significantly reduce the complexity to be required for implement the weights to the quantum circuit. And here we demonstrate some comparison between the we demonstrated some comparison between the our design and the previous design. And yes, if we can run this stuff. So here we provide a lot of function to support the implementation. Like we provide some control Z gate so that you can simplify to use this gate to control your circuit. And also we have some additional function. And here we are able to extract the data from the MNIST data set. Oops. Maybe we can wait a little bit and we can run this program out. And here, after that, we do some data pre-processing to integrate the data to our quantum circuit. And we're given the weights. And this one will be our non-optimized circuit. Actually, this implementation is what we see from this paper. We implement their design and as our baseline for the computation for our quantum circuit. And here we created the hidden circuit and the second layer. And here we also provide the optimized version that is based on our algorithm. And then we can see that okay. And we do some comparison between these two, and yeah, and we can see that for the non-optimized one, it obtains such kind of result, and for ours, we obtain a very similar result with this, but the circuit depth will be reduced from 58 to 38. And if you change the weight, the difference will be much more clear. And Okay, and we also do some result and analyze on the for the scaling. If we have our input size to be larger, we can see the red line represent our result. The y-axis represent the number of operator to be used that can be considered as the complexity, and the x-axis is related to our input size. As we can see, the red line is our result. The black line is one on the classic computer, and the blue line is the one we have already seen in this paper. And we can see, compared with the classic computer, we can see the number of operators to be used is dramatically reduced when we scale up the input size to more than 2,000 inputs. So in this tutorial, Collab, actually we provide such kind of comparison, and if you can run it at offline, maybe you can see we can plot the comparison result, which is demonstrated in our previous slide like this one. And finally, we also do some experiment on the MINIST data set, and we can see that when we have a larger structure and we can achieve more than 10 times reduction on the cost. And also our design can provide some kind of high accuracy compared with the same binary neural network on the classic computer. And here we also do something on the quantum real quantum processor provided by IBM. And here we can see in addition to the design, actually we also need to consider some error in the quantum circuit, and the graph D provides the information of the error for so each circle represents one physical qubit, and the color here represents the error rate on the physical qubit. And the connection represents these two qubits can talk with each other, so that we can apply the control X gate on these two qubits. And also the color represents the error rate between for this talk. And in addition to this, actually, we also need to map the qubit, the logical qubit to the quantum physical qubit. So that after we have such kind of mapping, actually we can run such kind of circuit on the real quantum computer. And this figure provides the golden result we want to achieve. And this result is conducted on the perfect simulation, and we can see the accuracy for this one is something like 98%. And this one we do not do some awareness of error when we do the mapping, and the accuracy is degraded to something like 68%. And for this one is our implementation. We run it on the real quantum computer, and we do the mapping, consider the error. And after that, we can resume the accuracy to more than 80%. So this is some result we conducted on the real quantum quantum computer. And maybe we can go back to see the result. Okay, so after we run the fifth tutorial, actually it can provide you a comparison between our QuantumFlow and other implementations. Okay, so here we are done the introduction of the QuantumFlow, the design of QuantumFlow. Is there any questions from the audience? Okay, so consider we are still we have already reached the 12, so maybe we can directly introduce our third session, that is build the quantum circuit for neural network acceleration using the QuantumFlow neural network. This is an API we just developed, and it has already been pushed to the PyPI, so that you can directly install our provided package, and then you can use the function. So in the previous tutorials, you have already seen that we have very long code to implement this stuff, but now we have such kind of package, and it can help you to simplify your implementation. And here we have the document for such kind of API, and if you see the module here, actually you can see that we designed the QF circuit, QF map, and the QF net corresponding to our QuantumFlow design framework. And we also provide the source code of our implementation. And if you have any questions, maybe you can put place some issues here so that we can resolve such kind of issue. And here is some introduction of the QFNN. We actually, for the QF circuit, we are built upon the Qiskit and also QuantumFlow, so that it can help you to automatically generate the circuit to be run on the IBM quantum computer. And the QFNet is based on the PyTorch and the QuantumFlow, so that it can build up the network that can be trained on the classic computer using the PyTorch. And the QFFB forward and backward is based on these three guys, and they can generate the network. And this network can be trained on the PyTorch framework, and also it can help you to prepare the data to be translated from the classical data to the quantum data. And finally, we have the QMap that integrates the algorithm proposed by our paper, so that you can directly use such kind of algorithm by just invoke this mapping U layer function. And after that, I would like to demonstrate some implementation using the library. For example, if we want to implement the QFPNet in our paper, that is based on our the probabilistic the random variable based quantum neural. If we want to implement one neural, actually we no longer need to write a long circuit design for the using the Qiskit details, but now we can only provide create such kind of circuit and also initialize the P neural circuit using our package, and then we can create the input qubit. You just need to pass the name for the input qubit and also the circuit you want to build on, and to this function, and also the auxiliary circuit and output circuit. And after that, the only function that you want to use is a forward function, so that it can help you to flow your design onto the circuit, and it will you need to provide the weight, the weight you want to do for the classic neural computation, and then all of this as the input we get, and this step, this is our input, and this is auxiliary qubit, and this output qubit, and after that you can draw the circuit. So we can so for this we can I believe we can run it very swift on the. We can terminate other sessions. Okay. Okay, so the thing like that, you can install our QFNN, and here we provide some weights, so that for the trained model, so that we can obtain some weights directly from the trained model. And after that, you need to import some function that you want to use from our package. And after that, actually you can we are given the weights. Oops, it's still running. Just wait a moment. Okay, great. We have loaded all the package, and then we have the weights, and then we see that we just create the we can just use the simple instructions to create such kind of quantum circuit that follow the same function that we have introduced in the QuantumFlow. so you do not need to hand code the details of the circuit design. And if we do it in the multiple layers, actually we can also extend such kind of quantum neural to implement the random variable based quantum neural in such kind of way. And we can do some simulation here, and also we can do the same thing on the classical, and we can see for the simulation, actually we have almost the same result compared with the class the value obtained on the using the PyTorch. So this one gives you an example how to use the library to create the P layer, and for the HNet we will apply the U layer. That is the one has the potential to achieve quantum advantage, and also we are given the number of the input neural and also the output neural stuff, and also we want to encode the weights to the circuit. And in our second example, actually you can see you can follow the very similar code as what we have already seen in the previous one, the very similar one. Just change the P layer to U layer, and you can obtain a U layer, and then after that you will do a forward to create the circuit, and after that you can run your circuit on the quantum computer. Yeah, let's complete this one, and I think the following will be very similar, and we provide such kind of example so that when you design your new, if you want to use such kind of quantum flow to design your own neural network, you can just follow such kind of example to build up any kind of architecture that you want to implement. So here we have the okay, maybe we can move further, and we can come back to see the result. And for the FB, actually, we provide the source code for training the neural network on the PyTorch, because on the training procedure, actually, we done it on the classic side, so that it is very similar as what we see for the training for the standard neural network. And the thing here is that we create a new net. So we will create such kind of net to create a model, and we will have some detailed discussing later in this tutorial. Maybe we can see whether we have completed. Okay, great. So after we load the model, actually we load the weight, and then we build the circuit. And so this in this way we build the second layer of our, so this is our first layer of circuit using the U layer, and this one will be our second layer, and it will end the P layers after the U layer without going through the classical computer. And after that we can do some simulation for the implemented quantum circuit for this one, and we can your guide how to use U layer to create the neural network. So beyond quantum flow, actually our package also include other component to support the implementation of other proposed neural network, quantum neural network. One is of FFNM proposed by in this paper. And here is an example to implement such kind of thing. And the other one is that we also implement the variation quantum circuit to for in the package, so that you can similarly do the similar thing, create the circuit and do the forward and provide the circuit that we have implement, so that you can create the circuit automatically without going to a lot of details. And finally, actually, our package also support our most recent work on QF mixer. And next session, we will introduce the QF mixer in details. Okay, so I think this is full of the third session. Do you have any questions? And maybe I can use this time for some clarification. Okay, if there is no questions, maybe I can stop sharing at this place. And in the following, we will, in our fourth session, actually, our session 4, actually, we will have two of our most recent work on the based on QuantumFlow. And two of my students will be here to present their work. Maybe Zepeng, are you here? And can you share your screen? Zepeng, are you here?
Hi, Dr. Jiang. Can you hear me?
Oh, yes. I allow you can share your screen. Maybe so you can share your screen and start the introduction on the QF mixer.
Okay. So I will share my screen. And okay, so hello everyone. So now let's move to the session 4 of this tutorial. In this session, we will talk about the future works of QuantumFlow. I will first introduce QF mixer, and then Zhiding will talk about QF robust and finally Dr. Jiang will introduce the other future works and the open questions. I will trigger the laser font. Okay. So QF mixer is a work to explore the quantum neural architecture based on the existing quantum neural designs. I will first introduce the motivation of mixing different quantum neurons to build a quantum neural architecture. Then I will propose the design principles for the mixture and also show the experimental results to you. Finally, I will also show you our APIs to explore the quantum neural architecture by mixing different quantum neurons with 2 simple demos on Collab. Before I present the work of QF Mixer, please allow me to briefly introduce myself. I'm currently a PhD student at ECE Department of George Mason University, and I'm also a graduate research assistant of Trey Kuber and Dr. Jiang's Quantum Classical Computer-Aided Design Lab. I got my master's degree from University of Pittsburgh, and I obtained my bachelor degree from Harbin Institute of Technology. My academic advisor is Dr. Weiwen Jiang. He is assistant professor at ECE Department of George Mason University, and he is also the founder and director of J-Cuber. Besides, my research interest lies in quantum machine learning for quantum computers and on-device artificial intelligence for classical computers. So now let's move to QF Mixer. First, let's look at the background and the motivation. Since QF Mixer is built upon the existing quantum neural designs, so we need to do a quick review of the existing quantum neural designs before we dive into the details of QF Mixer. The first quantum neurons I want to introduce is the variation quantum circuit based neuron. It is one of the most widely used quantum neurons, and note we will just call it phi neurons in the remaining of my talk. As you can see in the left figure, it reuses the inputs as its outputs, and it makes use of the entanglement from quantum computing to increase the model complexity. Since the learnable weights here could be the real value, the frequency-based QNN works well as a linear classifier. However, it cannot be extend to multiple nonlinear layers with low cost, which makes it perform worse on many machine learning applications with non-linearly separable datasets than the neural network with multiple nonlinear layers. As we introduced in the previous sessions before, QuantumFlow is a co-design framework to optimize quantum neurons and quantum circuits simultaneously. It customizes 3 types of quantum neurons for the optimization of quantum circuit design. The first one is P-neural, which we show in these 2 figures. If the input data has n features, P-neural will encode each feature as the probability of the one state of a qubit, and this encoding is called probability encoding. I think we have already mentioned that encoding method before, but we use the name angle encoding, but basically they are the same thing actually. In probability encoding, input data with n features will be encoded as quantum state with n qubits, and for P-neural, its input is encoding method for the input qubits and output qubits are both probability encoding. So this figure shows the quantum circuit implementation of P-neurals, and as it only since it only applies X gate to implement the weights of P-neural has to be binary. But since P-neural is easy to be stacked to form multiple nonlinear layers seamlessly, which is also a big advantage to handling more complicated machine learning tasks with nonlinear separable datasets. The second neural is U-neural. If input data has n features, U-neural will encode each feature as an amplitude of one basis state. This encoding method are called amplitude encoding. In amplitude encoding, input data with n features will be encoded as a quantum state with log n qubits. For P-neural, different from its encoding method for the input, it applies probability encoding to its output qubits. And these 2 figures shows the neural computation and the quantum circuit implementation of U-neural respectively. Since it only applies Z-gate and control Z-gate to implement the weight. The weight of U-neural is also limited to be binary, but U-neural could be connected to P-neural seamlessly. Thus, it could form a quantum neural network with multiple linear layers when combining with P-neural. Besides, it applies amplitude encoding to the input qubits. It could achieve quantum advantage. The third neural is N-neural. Its neural computation and quantum circuit implementation are shown in these 2 figures. The function of N-neural is like batch normalization used in neural network on classical computers, and it is optional to add it after P-neural or U-neural. Same as P-neural, N-neural encodes its input and output as probability. And this figure shows the circuit implementation of Q-neural, which uses one-to-one mapping for its data encoding. However, this encoding method is almost impossible to achieve quantum advantage. Moreover, it uses repeat until success to build a nonlinear function, which is not an efficient way. Q-nonlinear neural applies Boolean function to realize any nonlinear function. This figure shows 2 circuit implementation of 2 different nonlinear functions. However, this kind of neural design could not achieve quantum advantage. Q-artificial neural implements a binary perception in quantum computers, which is very basic in machine learning on classical computing. However, it requires its input and the weights to be binary, which restricts its application and representation capability significantly. There also exist many other works on quantum neural designs, and you can find such works cited in our paper. I listed the title here. If you are interested in other quantum neural design, please refer to our paper. The recent work on neural architecture search for neural network on classical computers shows that mixing different types of neurons could improve the performance of a neural network. Therefore, it inspires us to explore the potential of mixing different quantum neurons to form a quantum neural architecture. Based on our private discussion on different quantum neurons, we find that phi neuron and the neurons from QuantumFlow are complementary to each other. The real valued weights from phi neuron could increase the representation capability of the neurons from QuantumFlow, while the neurons from QuantumFlow could help the phi neuron to form a quantum neural network with multiple nonlinear layers with low cost. Therefore, we think that mixing phi neuron and the neurons from QuantumFlow is a good starting point for us to explore the mixture of quantum neurons. However, mixing different types of quantum neurons have many challenges. It could incur quantum classical communication overhead. It might also cause inconsistent design of the same type of neurons. Moreover, it could lead to inefficient training on classical computers. The details of these challenges will be introduced in the next part. So now let's look at the QF mixer, the quantum neural architecture design we proposed. Before we dig into the technical details of QF mixer, I should first clarify the design goals of neural mixture, which corresponds to the challenges I mentioned before. First, the quantum neural network formed by our quantum neurons should be able to run on quantum device only. A popular method to implement the quantum neural network is add measurement after each quantum neural layers and encode the measured output to input quantum states for the next quantum neural layer. This method is shown in this figure, and it will, as you can see, there is a classical computing part involved. So this method will incur expensive quantum classical communication overhead. When we design a neural architecture to mix the different neurons, we should avoid such costly overhead. The second goal is to ensure the consistency on the encoding method of neurons, regardless of its placement. For example, the figure on the left shows the neural computation of a P neuron. The figure on the right shows the corresponding quantum circuit implementation of P neuron. But this circuit implementation assumes that the input is encoded by probability encoding. So if you want to implement the same neural computation with different encoding method, when P neuron is placed in some specific layers of a quantum neural network, the circuit design should be built in a different way. However, this is very inconvenient and also bad for systematically building the blocks of a quantum neural network. Therefore, we want to keep the consistency on the encoding method of neurons, regardless of the placement. Since the near-term quantum computers has a limited number of qubits and high noise on each qubit, training quantum neural network on quantum computers is unstable and not scalable. Therefore, we usually need to train quantum neural networks on classical computers. However, directly training the quantum neural network without decoupling the neurons on different layers is costly, because the training overhead for each layer will increase exponentially as quantum neural networks go in deeper. In this figure, the above quantum circuit needs 2^6 by 2^6 unitary matrix to simulate this quantum neuron, while for the quantum circuit in the bottom, as you can see, it is actually the same quantum neurons with the same input. We only, but in the bottom circuit, we only need 2^2 by 2^2 unitary matrix to simulate the same quantum neuron. But you might notice that the output from the same quantum neuron is different in this example. It is because that in the above quantum neurons two input qubits are entangled or coupled with the other 4 qubits, the other 4 input qubits from the previous layers by the control X and the control Z gate, while in the bottom circuit, the input qubits are decoupled neurons, So the training overhead are decoupled with each other. Therefore, if we can make the input qubits decoupled with neurons in previous layers, then the training overhead will be decreased significantly, and it could be achieved by our QF mixer. This slide summarizes design goals of mixing different quantum neurons. To achieve the 3 design goals for neural mixture, we propose several design principles. If we follow these principles, the design goals will be achieved automatically. This figure is a visualization for the design goals. Each path in the figure represents a possible mixture of 2 quantum neurons. The 2 quantum neurons are denoted by QN1 and QN2 here. Note that in this figure, the P denotes probability encoding, and A denotes amplitude encoding. Assume QN1 is a quantum neuron in a specific layer, then QN2 will be the quantum neuron in the next layer. The first principle corresponds to paths 1 to 4 in this figure. It actually means then corresponds to the case where the output qubits of QN1 are not entangled. In this case, since the output qubits from QN1 are decoupled with the output qubits of its previous layers, arbitrary mixture of quantum neurons is feasible, regardless of their encoding method. Then I will discuss the case where the input qubits of QN1 are entangled, and we will have principle 2 to 5. Principle 2 corresponds to path 5 here. The case where the encoding method for the output qubits of QN1 is amplitude encoding, and the encoding method for the input qubits of QN2 is also amplitude encoding. In this case, since there is no probability encoding involved, there is no requirement on the decoupling, so this type of mixture is feasible. The principle 3 corresponds to path 6, the case where the encoding method for the output qubits of QN1 is amplitude encoding, while the encoding method for the input qubits of QN2 is probability encoding. To tell whether this path is feasible, we should take a look at a special case where QN1 is just a feature in the input data and QN2 is a neuron in the first layer of a quantum neural network. In this case, to apply the probability to apply the probability encoding on the input data, the input qubits are required to be independent of each other. And based on the goal of consistency we mentioned before, when QN1 is the neuron in other layers, the independency requirement should also hold. However, since the output qubits of QN1 are entangled in the path 6, so these qubits are not independent to each other. Therefore, the requirement is not hold, and this path is thus infeasible. Principle 4 corresponds to path 7, the case where the encoding method for the output qubits of QN1 is probability encoding, while the encoding method for the input qubits of QN2 is amplitude encoding. Whether this path is feasible is conditional. If for the input qubits of QN1 are reused by the output qubits, such as the phi layer, then this path is feasible. Otherwise, this path is infeasible. Principle 5 corresponds to path 8, the case where the encoding method of output qubits of QN1 is probability encoding, while the encoding method for the input qubits of QN2 is probability encoding as well. Whether this path is feasible is also conditional, and I listed 2 conditions here. If the output qubits of QN1 are used as control end without a phase kickback, then the path is feasible. Or if the operation on the output qubits of QN1 only be rotated by around x-axis in QN2, then this path is also feasible. Following all the design principles I just introduced, we propose QF mix NN, a quantum neural architecture design based on the mixture of different quantum neurons. This figure gives an overview of QF mix NN. As you can see, the neural computation part is conducted purely on quantum devices, while the data preprocessing and post-processing part are conducted on classical devices. In the neural computational part, the phi layer should be placed as the first part. The phi layer consists of phi neurons, and the phi layer will applying amplitude encoding to the input data. I used R1 to denote the number of phi layers in the QF mix NN in this figure. The extreme case of QF mix NN is that we only use phi layers by setting the R2 and R3 to 0, which we will introduce later. For the part of phi layer, the larger R1 is, the more real valued weights are provided in the neural architecture. After phi layer, a U layer is optional, which consists of U neurons. We use R2 to indicate whether we add U neuron after phi layer. So R2 is a binary number. When R2 is 1, the U layer is added, and the U layer will provide the non-linearity to the phi layers. After the U layer, we can add a stack of blocks made up of N layer and a P layer, which consists of N neuron and P neuron respectively. We use R3 to denote the number of such blocks. The larger R3 is, the more the QF mix NN will provide more nonlinear layers. After we have the picture of the QF mix NN, I would like to emphasize that the QF mix NN follows all the principles we proposed before. Here I listed all the possible mixture that might appear in QF mix NN. The first 2 mixture follows path 5, which is feasible. For example, as you can see in this table, the phi neuron could encode its output as amplitude, and the U neuron could encode its input as amplitude. That's why I say the phi neuron to N neuron corresponds to path 5, and path 5 is feasible. The last 3 mixture all correspond to path 8. You can verify my statement by using this table. Since the output qubits of U neuron, N neuron, and phi neuron are used as control end without phase kickback, the condition of path 8 are satisfied. Therefore, such a mixture are feasible. After the technique part of QF mixer, now we can take a look at the experimental results. So this table shows the experiments of QF mixer, QuantumFlow, and the VQC based QNN on 5 different data sets. Here, the evaluated data set MNIST X represents a subset of MNIST with X classes. For example, when X equal to 3, MNIST 3 represents a subset with 3 classes. As you can see in this table, neural architecture from QF mix outperforms the other neural architectures except for MNIST2. In MNIST2, VQC based is the best. This is because that MNIST2 is a quite simple dataset which is closely to be linearly separable, and the VQC based neural network, quantum neural network, is quite good at such tasks. However, in MNIST, which contains 10 classes and much complicated than MNIST2, architecture from QF mix outperforms the other neural architectures significantly. It could achieve more than 90% accuracy, while for VQC based QNN it only achieved about 53%, and for QuantumFlow, for the quantum neural network of QuantumFlow, it only achieved about 70% of accuracy. From this experiment, we can conclude that non-linearity is important. A linear decision boundary is not sufficient for completed tasks, and the real valued weight is helpful. It increased the representation capability of QNN significantly. The high accuracy of QF mix NN shows that the QF mix NN could take the advantage of both VQC-based QNN and QFNet from QuantumFlow. Besides, we also conducted several experiments to explore the impact of number of phi layers, the R1 value, on the accuracy. As you can see that in these two figures, there is a trend that increasing the number of phi layers could improve the accuracy of QF mix NN further. Finally, I would like to introduce the API of QF mix NN we provided. So the CQFmix.net is a module designed for QF mix NN. It is a submodule of QFNN.QFFB. The input parameters of this API is listed here. The first parameter is image size, which we will pass an m. If we pass an m to this parameter, it means that the image we will process is m by n. Then there is the second parameter is layer, which is an array describes the architecture of QF mix NN. The neural we currently support is phi neural. There are two versions of phi neural, which is phi 5 and phi 10, and U neural, and P neural, and also N neural. That's all of the neurals we supported yet. The third parameter is training. It is true if you want to train the QNN. Otherwise, if you only do the inference, you will just set it to false. The binary parameter means indicate whether the input image is binary. And as for the given angle and the train angle parameter, it is only available when you specify a neural in the architecture of QF mix NN. And given angle, for a given angle, you should give the initialization angle for the N neural. And if you want to train the angles in the training process, you should specify you should set the train angle parameter as true. The forward function of the net module will take a batch of encoded input images with size of m by m and output a batch of the corresponding prediction results. So this slide shows an example where we mix the phi layer and the U layer. the parameters layer will specify the architecture of the QF mixer. And as you can see here, the array this array corresponds to a quantum neural network with a phi layer, which has 4 output qubits. Since phi layer encodes its output as amplitude, and the 4 output qubits has 16 amplitude, we specify the number. That's why we use a 16 here to indicate that the phi layer has 16 amplitude. And then we add U neural with 2 U layer consisting of 2 U neurons for classifying. After building the necessary parameters for the net module, we will build a model using the net module, and as you can see in this line of code, and then we can load the pre-trained parameters to our module and encode the input to quantum state. After all this preparation, we can put the input to the module called the forward function, and the output will be the inference result for the input you passed in. This slide is another example about mixing U neural and phi neural. Note that for this mixture, it is actually not follow the design rules we proposed before. So it actually so if you want to make it feasible, you actually need measurement between the U layer and the phi layer. So that's why we have a conversion layer here, which will convert the probability from U neural to the amplitude as the input to the phi layer. So for the layer parameters here, we have the first layer is U neural, and it has 4 output. It has 4 output neurons, and then we do a conversion, the measurement, and to convert the 4 output qubits to 16 amplitude, and then we add a phi neural. We add a phi layer to accept such inputs, and we will use two qubits, two amplitude from the phi layer as to specify the architecture, or to specify the classification of the output. So the remaining part is basically the same thing as we introduced in the previous slides. So now I want to show you the example in the collab to see how it works in how to use our API. But sorry, maybe I need to wait and do it again. Okay, so I think so. Now the first example is to build the circuit of phi layer and the U layer. First, we need to prepare the environment and define the necessary parameters for the input data set. So I think we need to wait for some time. Okay, still need some time to install the necessary packages. So now all the necessary package is downloaded, and then we initialize the parameters for the data set. And now we need to load the data. And also load our pre-trained model parameters. So here in this part, we use the net API I just mentioned to simulate the inference of QF mix and learn on classical computers. So, as you can see that the classical inference result is shown here. And I will copy this result. Then I want to show you that we will build a quantum circuit corresponding to the QF mix and learn here, and run it on the quantum simulator. As you can see, this is the quantum circuit for our QF mix and learn. Finally, we run it with 10,000 shorts, and we will see the simulation results here. I would like to add a new cell here and copy the result from our private API here. As you can see that this result is very close to the simulation result. And if we increase the number of the QC shorts, they will become more closer to each other. So this verifies that our implementation of the QF mix API is correct. And similarly, I also want to show you another example for the U layer and the V layer.
Yes, so maybe we can lift this this part, and maybe we can move to the next topic.
Okay. So basically, actually, this example is the same thing. Yeah.
Right.
And finally, I want to briefly give you some more examples about how to use the net API. Actually, the key point to use the net API is that we need to build the parameters layers. After since this is the main difference for different neural architecture. The other part, we just could remain unchanged. So for the first line, it corresponds to the quantum neural with where we mix the phi neural and the U neural. It means for here it means that the phi neural the first layer is phi layer, and it has 16 output amplitude, and the second layer is U layer. It has 2 output U neural. The second line corresponds to the case of phi layer added by P layer. The first layer of P layer, since in this case the phi layer will use the probability encoding for its output qubits. So here we will specify that the phi layer has 4 output qubits, and as for the second layer is P layer, and the P layer has 2 neurons. For the third case, where the first layer is phi layers, it has 16 amplitude, and the second layer is U layer, it has 4 U neurons, and the third layer is P layer, it has 2 P neurons. And the last two examples is actually similar to the 3 examples I just introduced. These 2 examples is just want to show you that we can add multiple phi layers and multiple P layers in our in our exploration of quantum neural architectures. I also want to kindly remind you that currently in our API we did not implement logic to judge whether the input layers, the neural architectures you passed in, follows the design principles we proposed. So it might happen that you actually pass an illegal layers, but without get any error message, and then you get some weird outputs, which we don't know what that means. So that's all I want to talk about the QF mixer. So I will leave the time the next time to Zhiding to talk about his work on QF robust.
Sure, thanks, Zepeng. Yeah, maybe we can continue and complete the last part. Actually, the QF robust is very interesting because for the current quantum computer, it has a very high noise. So that if we design a neural network for the quantum computer and we cannot handle the error, that will be we cannot get the correct result. So Zhiding will present his work recently and demonstrate how can we learn such kind of error information into the quantum neural network. Zhiding, if you are ready, maybe you can start sharing your screen and start the talk.
Yes, thank you so much. I'll
by the way, maybe we will run a little longer than the planned time. But if you have interesting, feel free to remain. And if you have other thing, maybe feel free to leave. No problem. Thank you.
Oh. So I'll continue to talk about the QF robust. This topic, we discuss how to learn the error into the quantum neural network. And I'll start with the motivation, challenges, and then the technical part, and finally the results. There is a short biography of myself. My name is Zhiding Liang. I'm currently a graduate assistant in Sustainable Computing Lab. I'm a first-year PhD student, computer science and engineering at University of Notre Dame, and I received my BS in electrical engineering from University of Wisconsin-Madison. And I'm co-advised by Professor Yush in University of Notre Dame and Professor Weiwen Jiang in George Mason University. My research interests focus on the quantum machine learning and the quantum compiler. Before I talk about the quantum, talk about the motivation of our work, I want to build a simple background of the quantum errors. Before we can access into the fault-tolerant age, we will stay in the noise intermediate scale quantum NISQ age for several years. And in NISQ age, quantum device always has really high error rate. I give an example of a true quantum machine here. We can see in this graph, the error rate in this quantum machine is 10 to the negative 4 to 10 to the negative 2. And as we all know, a bit in the traditional CMOS device always with the error rate about 10 to the negative 15. It's a really huge gap from the qubits to the bits in the traditional CMOS device. 10 to the negative 2 to 10 to the negative 15. So the noise is a really big problem when to solve in the NISQ quantum machine. And I also want to introduce two common types of the quantum errors. This is also two types we use in our quantum simulator. Bit flip error and the phase flip error. Let's assume this is a perfect quantum circuit. It's a X gate, just And what the bit flip arrow do is actually address an extra X gate on the original circuit. What is this X gate do is like flip the state from 0 to 1 or flip the state from the 1 to 0. This uppercase E here is the error rate determined by the qubit mapping. And if we assume this error rate is 10%, which means we have 90% probability to get the circuit run on the correct way, and 10% probability we get the original circuit with an extra X gate. The only thing different between the phase flip arrow and bit flip arrow is like phase flip arrow address an extra Z gate instead of the X gate. This Z gate, what is this Z gate do is like make a phase shift among the Z axis. So, which means if there is the error rate, there will be like a wrong circuit, with the original circuit and the extra Z gate. And why error need to be learned in the quantum neural network? We do a simple experiment based on the QuantumFlow and use the MNIST dataset. I change the noise model like bit flip arrow, phase flip arrow, and the bit phase composed arrow. And we change the affected gates, the affected qubits, and we change the error rate and get the prediction accuracy result. From this table, we can clearly see the noise significantly affected the quantum neural network. And we also learned there's some work already done that learn the error into the classical neural network. So we just consider if we can learn the error into the quantum neural network. This is the motivation of our work. And then I'll introduce the challenges in learning error rates into the quantum neural network. For the first challenge, I want to give an example. Let's assume this is a quantum circuit generated by a quantum neural network. And we assume the logical qubit Q0, Q1, Q2, Q3 mapping to the physical qubit P0, P1, P2, P3. And the gate in the same color dotted box is corresponding to each other. Let's access to the first gate in the red dotted box. To process this gate, we require the Q0 connected with the Q2. But we can see the initial position Q0 is not connected with the Q2. So we need to address a swap gate here to make the Q0 towards the Q2. And after the swap operation, we can see the Q0 is connected with the Q2. So this red box gate can be successfully executed. And then we look at the gate in the green dotted box. This CX gate need Q0 connected with the Q3. And we also address a swap gate to make the Q0 and Q2 exchange the position. At this time, Q0 is connected with the Q3, and this gate in the green box can be successfully executed. And the orange box gate is like it's pretty similar operation. We apply a swap gate between the Q1 and Q2, make the Q1 and Q0 connected, and we can process this whole quantum circuit. And this bottom quantum circuit, we assume this is from a same quantum neural network with the upper quantum circuit, but generated by the different training weight. For this quantum circuit, the difference with the upper quantum circuit is there is no medium green box gate. So after we process the red box gate, it is actually a same operation with the last one. And when we directly go to the orange box gate, we found the Q0 and Q1 is already connected. So this orange box gate can be directly executed. From this example, we can see even the quantum circuits from the same quantum neural network. Because of the training weights change, the quantum circuit may change, and the information contained in the same physical qubit also can be changed. For example, this Q0 is contained the Q2, and this P0 is contained the Q1. So we found the challenge. The error is unpredictable on the quantum circuit, even they're from the same quantum neural network. So we need to fix the logic physics qubits mapping. And the second challenge is that it is a time problem. The whole process time is equal to the training time plus the compiling time. And currently, the training neural network work is time consuming. And unfortunately, the existing quantum compiler are also always time consuming. It is not doable for the NISQ quantum machine if we apply a time consuming stuff into another time consuming stuff. So the second challenge is existing compiler may not suitable for training because they're always time consuming. We need to build a compiler with faster compiling speed. And this is a general framework we proposed, the quantum error-aware training framework. So firstly, we have a quantum neural network, for example, the QuantumFlow, and they provide the training weights. These training weights generate the logical quantum circuits. And we put these logical quantum circuits into the application specific mapping. This is a mapping method we proposed to fix the logical to physical qubit mapping, and I will discuss it in the next slide. After the logic to physical qubit mapping, we get the physical quantum circuits. We put the logical qubits into the physical qubits. And then we use these physical quantum circuits to interference with error aware on the true quantum machine or the quantum simulator to get an output as the model accuracy. We use this model accuracy to train the quantum neural network to learn the error information and update the training weights. So this is a loop. Here is the first technical part, training the quantum neural network to learn the error information. I think the quantum error-aware training framework in the last slide can be better to understand as the following equation. So CI is the logical quantum circuit generated by a specific training weights provided by the quantum neural network. And MI, you can take this as a physical quantum circuits, and this is represented as the logical quantum circuit CI mapping to the physical qubits, and the EI is the error model based on the MI based on this quantum this physical quantum circuits. And AI is the accuracy of the quantum neural network with this specific training weights, and executing by the physical quantum circuit MI and the error model EI. Since we have the model accuracy, we put this into a deep learning neural network, for example, the RNN, and we have the search weight. This search weight means the training weights has the best performance under current noise condition. And once we have the search weight, we update this to the training weight and continue to another iteration. And the second technical part is the application specific mapping. It's the mapping method we use to fix the logical to physical qubit mapping. And as Professor Jiang mentioned before, the QuantumFlow always generate the quantum gates as a CZ, CCZ, CCCZ, and so on. So we take the CCCZ as an example to illustrate our mapping method. And this part on the right is the decomposed version of the CCCZ gate. We also use a decomposed version of the CCX gate to help you to better understand this mapping method. So there has in total 6 basic CX gates. we list them as the G1, G2, G3, G4, G5, and G6. We assume the initial mapping is like from the logic qubit Q0, Q1, Q2, Q3, AX0, AX1 to the uppercase corresponding each other. And let's look at the T1. T1 is a CCX gate. And at this time, this CCX gate is actually addressed on the Q0, Q1, and the AX0. So let's look at this corresponding decomposed version. Process the T1 CCX gate is actually process the 6 basic CX gate. So for the G1, G2, G3, G4, we require the Q0 connected with the AX0 and Q1 connected with the AX0. We can see in the coupling map, the Q0 is already connected with the AX0 and the AX0 already connected with the Q1. So the G1, G2, G3, G4 can be directly executed. The only thing left is the G5 and the G6. So G5 and G6 requires the Q0 connected with Q1. We decide to use a swap operation to make the Q1, to make the AX0 towards the Q1. After the swap operation, we can find the Q0 is already is connected with the Q1. So G5 and G6 can be successfully executed. And then the T2 and T3, the CCX gate in T2 address on the Q2, AX0, and AX1. We can find that the Q2 is already connected with the AX1, and AX0 is already connected with the AX1. So G1, G2, G3, G4 can be directly executed. This is actually similar with the T1. So the only thing we need to do is address a swap gate between the AX1 and Q2. After swap operation, we can find the Q2 is connected with the AX0. So the CCX gate in T2 can be also executed. And at this time, the T3, the CC gate, requires the AX1 connected with the Q3. This is also already connected. So T3 can be successfully executed. T4 is kind of like a backward operation of the T2. This is this step is different with the last two steps, because if you look at the G1 requires the Q2 connected with the AX1, and G2 requires the AX0 connected with the AX1. We can find this time AX0 is not connected with the AX1, so we put a swap gate between the Q2 and AX1. After the swap operation, the G1, G2, G3, G4 can be successfully executed. The thing left is the G5 and G6. And for this G5 and G6, they require the Q2 connected with the AX0. For this step, we do not use the swap gate. We use the bridge gate instead. The bridge gate has the property. If the middle qubit state is 0, the bridge gate only consumes 3 basic CX gates. But if we use the swap gate here, because we want the qubit back to their original position, so we need to use 2 swap gates here to finish to match the requirement. 2 swap gate means we need to consume 8 basic CX gates. But we use this bridge gate consume 3 basic CX gates that save the number of extra gates. T5 is similar with the T4. So it's a backward position of the T1. We address the swap gate between the Q1 and AX0 to fit the requirement of the G1, G2, G3, G4. And then we use a bridge gate to connect with the Q0 and Q1 to executing the gate G5 and G6. After these operations, we found the final mapping is as same as the initial mapping, which means we fix the order of the logical to physical qubit mapping. We make the gate fixed, and the error can be predictable. After the technical part, I want to show some QF robust results. The first result is based on the IBM quantum simulator. And this baseline has the initial weight. And this initial weight is the one with the best performance under the perfect model. The perfect model means there is no error. And there is another observation. When we increase the error rate on the quantum simulator, the QF robust pushed the improvement on accuracy up to 28%. We also do some comparison of existing compilers with ours. We choose the QU-EKO and the HA, two existing compilers, and from this result, we can see ours has like pretty much shorter elapsed time compared with the two existing compilers. And because of the QU-EKO shows like a pretty long time to compile the complex quantum circuits, so we do not take it as the comparison as the next step. The last comparison we do is compare the existing compiler HA with the same model on the IBM Q material with ours. And we found that ours, this results demonstrate some advantages of ours compared to the HA. We have the higher accuracy. Like we have like 5% accuracy advantage compared to the HA. And we have less extra swap gates, which means we have like less consuming. And we have the shorter elapsed time. We do the 0.014 second, and HA achieves 3.955 seconds. These all results all demonstrate that we have built a high efficiency quantum compiler, and combined with the like application specific qubit mapping method, we can achieve our ideas to solve the challenges. And this is all about the QF robust NN I present today. And I think Professor Jiang will continue to talk about the other future works.
Thanks, Zili. Yes. Thanks so much. And yeah, actually, I think we have already run out of the time. And so here, I would like to finally share my screen to point out some places that you can find a lot of resources, and all of our slides will be uploaded to our website for the QuantumFlow website, and you can find a lot of materials like the slides here. And since we have already run out of time, maybe I think it would be good if some of you want to come up, and if you have any questions, we can discuss, and so that we can also include some future work. So any questions, feel free to unmute yourself, and we can have a brief discussion, I believe, maybe in 10 minutes. Yes, maybe we can have our first questions. Anyone want to talk about something? If you have any questions, feel free to unmute yourself. Maybe if we do not have the first question, how about the second question? Okay. Okay, so Yeah, so if you have further questions on the QuantumFlow and also how to use the QFN the QFN package, feel free to contact our lab or directly contact me, and I believe that we can point out the corrected resources that you can allocate you can find to solve your problem. And thank you so much for joining this tutorial. And yeah, I think we cover a lot of things, and maybe we can end at this place if we do not have any questions. And thank you so much for attending, and have a good weekend. Okay, thank you. Maybe we can end at this place. Goodbye.